Please welcome the 9th President of the California Institute of Technology, the Sonia and William Davidow Presidential Chair and Professor of Physics, Dr. Thomas F. Rosenbaum.
Great. Thank you. Well, really kudos to you, and it's just wonderful to have you back on campus. We've enjoyed it so much. At the Half Century Club celebration last night at our home, I asked how things were going, and one of the people I talked to said, oh, they're just great meals, one after another, and obviously many other things, but this morning is, by contrast, your intellectual repast. And this is something that's very important, of course, for you as alums and for us as faculty and administrators at Caltech to share the important parts of our mission of discovery and education. So I wanted to start with a quote from the polymath Leonardo da Vinci, who actually I think would have fit in beautifully at Caltech, with his eclectic interests in crossing disciplines, writing and code. He probably would have picked locks. And he said, "It had long since come to my attention that people of accomplishment rarely sat back and let things happen to them. They went out and happened to things." And I think that's a perfect description not only of our students today, but of our alums. You have gone out and changed the world. You have gone out and used the skills that you have obtained at Caltech to be able to think deeply about problems. And we continue that tradition. And I can tell you, and you'll hear today, that this is a fantastic time to be doing science and engineering. I know there's all the foofara and the rhetoric about difficulties and attacks on universities and everything else. But fundamentally, the questions that we're able to address now, the tools that we have, are just extraordinary. Whether it's the question of life on other planets, orbiting other suns, whether it's the emergence of quantum computers with its genesis actually with Richard Feynman here, among others, whether it's harnessing AI in all kinds of disciplines and putting together imaging and genomics and proteomics for personalized medicine, these fields are changing incredibly quickly, and Caltech is at the center of it. Today you'll hear not only from some of our faculty who are talking about this and talking also about the implications of these discoveries to society, but you'll have the pleasure of hearing from our graduate students, and there is the future. So thank you so much for coming. Kathy and I are looking forward to this morning as much as you are, and it's now my pleasure to turn over the podium to Sandra Tsing-Loh, who is a distinguished alum, a radio commentator, and a Caltech presence. Short and sweet. Thank you, Steve.
Thank you so much, Professor Rosenbaum, for kicking us off. And we have to say, your ability to combine poetry and science, citing Leonardo da Vinci, coming up with comments that are so eloquent, insightful, and moving, and in final draft form. And I can tell you right now, no speech here, no AI, no notes. This is President Rosenbaum's off-the-cuff, beautiful comments that we will miss a lot in the next, after your 12 years here. So thank you so much for inspiring us. No notes, amazing. We'll see you around campus, Professor. And now, good morning, Caltech alumni, families, and fellow travelers in the great migration of curiosity that is Seminar Day, right here on the campus that taught all of us to question everything. First joke of the day, get ready. Okay, to see if you're awake. To question everything except the parking signs, which remain Caltech's most rigorously enforced theorem. Let's try that again. Caltech's most rigorously enforced theorem. It'll go faster. Fantastic. Okay, I'm Sandra Tsing Loh, introduced by our president. Thank you so much. And also host of the Lowdown on Science, a daily NPR show that Caltech created over 20 years ago. This is my sixth year as your seminar day host, an event brought to you by the Caltech Alumni Association. Please join me in thanking the CAA team on the ground and up above, and production crew who make this whole thing run. Thank you. We have 400 of you on campus today, techers from every era, current students, postdocs, faculty, and families joining Seminar Day Kids. It's a new innovation. I saw some kids out there going, where's the kids section? And so that's exciting, and welcome, Caltech's youngest potential graduates, now in its second year. To everyone who traveled in, welcome back. To everyone joining online from everywhere on Earth, possibly beyond, welcome. Today's program features faculty from 6 divisions: AI and mathematics, the statistics behind US elections, the hidden choreography of electrons, the origin of life, vaccines that could help prevent the next pandemic, and materials that flow like sand and act like steel. You'll also hear from student speakers and our 2 elective blocks, check out lab tours, and after lunch, we'll announce this year's Distinguished Alumni Award and Chang Career Exploration Prize recipients. So a few quick housekeeping notes. First of all, cell phones, here. What do we know about cell phones? You can actually keep them on because Slido is back. You'll see a unique QR code for each session on the slides and printed in your program. Scan it, type in your question, vote on others. You can also include your class and in class year and your name, or stay anonymous. So phones today are encouraged, but please keep the ringer off. For restrooms are in the Beckman lobby out there beyond the green exits that are notated there. And if you're home, watching us from home, we hope you know where your bathrooms are. Let's try that again. If you're home, we hope you know where your bathrooms are. See how much, doesn't that feel better? Laughter is very healthy biologically. Okay, electives. We have 2 student-led electives, one before lunch and one after. 3 options each block. The 3 options are each block. There are 3 options on each block. The 3-minute thesis challenge, the Everhart lecture, and the Perpall surf speaking competition. You attend 2 out of 3 across the day, so you can sample more than one. Locations are on screen and in your program. Lunch and lab tours are on Beckman Mall and across campus from 12:20 to 2:20. Some tours have requirements: closed-toed shoes, gowning, the ability to take stairs, so double check the program before you sign up. After the second election block, we'll reconvene here at 3:10 sharp for exciting announcements, and then we'll do a deep dive into the origin of life. After that, 2 more faculty sessions take us to 5:30. Right after we close, everyone here is welcome to, in Beckman here, is welcome to join us for dinner out on the Beckman Mall. We hope you'll stay, keep the conversation going, and enjoy a little more time together on campus. Each faculty session ends with a Q&A and a 10-minute break. Are you ready? Okay, one more time. Are you ready? Yay! Okay, let's start with mathematics, AI, and the question of how machines are changing the way humans search for proofs. Our first speaker is Sergei Gukov, the John D. MacArthur Professor of Theoretical Physics and Mathematics. Sergei is a theoretical physicist and mathematician who spent his career building bridges between mathematical physics and pure math. Like pure math, okay? He earned his PhD at Princeton, spent 5 years at Harvard as a Clay Mathematics Institute research fellow, and 2 more at the Institute for Advanced Study before coming to Caltech. In recent years, he's turned to a different kind of bridge, connecting mathematics to machine learning. His talk today asks the question many of us may be asking in one form or another: where can AI genuinely help with discovery, and where can the heavy lifting be done by human intuition? Please give a big warm welcome to Professor Sergei Gukov.
Thank you, Sandra, for a very generous introduction. Thank you all for coming. Thank you, Professor Rosenbaum and Caltech Alumni Association for putting together this wonderful event. It's a pleasure and honor to be here. I came to Caltech first time about 30 years ago. That was 1997 as a prospective graduate student. And I didn't choose to go to Caltech at the time. I went to Princeton, but fate and destiny was still there. So my advisor actually then 2 years later came to Caltech and brought me along. And essentially ever since I stayed at Caltech. So no matter how hard I try to get away, my foot is still here. So as Henry mentioned, I started my path in mathematical physics, then shifted a little bit more toward pure mathematics, connecting different areas within mathematics together. And about 7 or so years ago, I wanted to try out AI, machine learning research, mainly to convince myself that this is all hype and I don't need to learn it. So unfortunately, I did the social experiment on myself and convinced myself that, yes, it is helpful. And I stayed in that research for past 7 years or so. During this time, I was very lucky to participate in large industry-scale projects that led to various AI systems that do mathematical reasoning. Some of these projects took up to 2 years, which actually is a lot by modern standard in AI research. And here at Caltech, exactly a year ago, we started a new lab in the Division of Physics, Math, and Astronomy, not in CS, but in math, which connects mathematics and AI. So the goal of the lab is to pursue building systems that are capable of mathematical reasoning. And that's going to be the subject of this talk, so I'll tell you a little bit about what the lab is doing. One thing I want to say is that Caltech is a very unique place, and given how fast everything is moving, this could only happen at Caltech. In fact, also thanks to your general support and participation, so some philanthropic contributions were extremely helpful in getting it off the ground very fast. And even though it's been only a year, the lab was pretty successful. So now there is strong push to either turn it into a company or scale it further. So we're actually, I don't know what the right word is, either competing or collaborating. I like to look at it as collaboration with big players, including even Google or some other companies I mentioned. So the question I want to ask today, or give you a kind of summary of what will it take for AI systems to do mathematical reasoning? So that's the question I want to ask. And we have to distinguish what mathematical reasoning is. So mathematicians are very precise, so we want to define everything. So I want to define my question a little bit more accurately. And when we talk about mathematics, of course, there could be like elementary school math. 1 + 1 = 2. That's fine. AI systems, general purpose AI systems can easily do it. And then it took about 2-3 years to graduate from one stage to the next in this hierarchy that's outlined on the slide. To go from elementary school to middle school took about a couple of years. Another couple of years to get to high school, then Math Olympiad competitions, undergraduate level. And this hierarchy continues. So then we need mathematics for something that would be worthy of a PhD thesis work in math department. So that's actually quite challenging for graduate students, so they spend the entire PhD graduate study to get to that point. For professors, there is a next level kind of problems that we solve on a daily basis, something that takes maybe a couple of months for us to resolve. So then we get to much higher level, which maybe is worthy of a Fields Medal or a paper in a very prestigious journal, and Millennium Prize problems in mathematics are definitely in that category. So the last two columns, or grades in this hierarchy, I would say would be worthy of a pretty substantial prize. And the other dotted line on the slide indicates roughly where general purpose systems are right now. So if you use something off the shelf that's publicly available, even if it's a paid version, it's probably going to be somewhere there. So there is obviously a gap, and as I said, this line keeps moving every year. And the question that many ask, both in Silicon Valley and also we ask in this lab here at Caltech, is what will it take, if at all, for us to get to this most challenging level? I want to preface this by saying that actually, after working on this for 7 years, I'm not convinced. I see a possibility that we won't get there in the near future. So that's why I want to ask, what is missing? Why we are not there yet? I don't want to speculate how long will it take, because, again, there is a viable possibility that we may not even be there. So since I was working on mathematics as a normal working mathematician, basically what I'm trying to build is an AI system that would perform at a superhuman level, so will replace myself. And the initial question is, why am I doing this? Honest answer, I don't know. It's just curious. So this is a good example of curiosity-driven research. Maybe a more serious answer is that if we build a system which performs essentially everything I was paid for in the previous 20 years, so maybe Tom won't pay me anymore once we build the system, we actually understand AI much better. We'll understand why it works, how it works. So by building it, we'll have more in-depth understanding of what it really is and what it can do, cannot do. And this reminds me of what Steve Jobs said about graphic user interface. So when he was trying to introduce it to his team in the early days of Apple, people on his team told him, Steve, it's going to blow us out. And his response was, it's better we do it than somebody else does it to us. So that's maybe kind of second iteration of the answer to this question. But the question is very nuanced, and I'm not going to go into it in this talk. I'll be happy to discuss it during Q&A. So going back to progression of AI from mathematical reasoning, I mentioned that it takes about 2 years to graduate from one stage to the next. So a natural question is this trend going to continue? Will the curve continue going at the same roughly linear pace? And that's not obvious at all. So for AI systems, there are roughly 3 components that have to be together and working well, and we need to make progress on each one of the 3. So one is data, another is compute, and third is algorithms and basically software. Algorithms, architecture, what drives the AI system. So this talk is going to be about the last component. This is what AI researchers like myself spend time on, thinking and inventing better algorithms. And the goal of the talk is to explain that we need more. We need ideas. So it's not just about scaling compute. But going for a second to the other 2 components, compute certainly helps, although its effect is logarithmic. There are this very standard logarithmic scaling laws in AI research, and it requires a lot of compute to make incremental progress. So now we're talking about putting data centers in space, and that's basically the reason. And another component I mentioned is data, and this is also kind of a tricky and somewhat controversial topic because at this point, most AI systems already scraped all of the World Wide Web. So the question is, are we running out of data? And this company, Epoch AI, with which we collaborated in the past, and I'll refer to this company at another point later in the talk, did some very thorough studies. And again, everybody likes to make predictions and assessments, so this was a pretty careful study. And they even are willing to predict when the data curve will plateau. So yes, with data centers, it's obviously a challenge, but there are many smart people who are trying to solve it. With data, it's kind of a challenge, and it's not entirely clear how to solve it. In mathematics, there is maybe a chance because mathematics can be augmented by synthetic data. And here we may have maybe some additional mileage, but this is very special to mathematics. So as I mentioned, the goal of this talk is to actually now focus a little bit more on the third component. Can we advance AI to get to this superhuman mathematical reasoning, and how can we do it through algorithm development? So can we invent new algorithms, and what's missing, what do we need to do? I don't really need to explain Hodge conjecture or Riemann hypothesis to deliver the key point of the challenge here, because everything we do in mathematics is finding a path. So a mathematician is basically a pathfinder from A to B. So usually A is some assumptions of a theorem, and B is the statement of the theorem. And our job is to find a sequence of logical steps that take us from A to B. And that's it. That's really how every math paper is written. So it's just a sequence of logical steps. So mathematicians are pathfinders from hypothesis to the goal, to the destination. And what distinguishes these different grades of elementary school, middle school, or professional mathematics is how long or complicated it is to find the path. Obviously, simple theorems that we learn in school have very short proofs. They may have 10, 5, maybe 30 steps. Proof of Riemann hypothesis that nobody has found yet, but community believes that it exists, is probably very long. It may have millions or maybe even hundreds of millions of steps, logical steps. So in mathematics, sometimes we play with examples and counterexamples, and those are also usually searches of the same kind of type. So that's why, for purpose of this talk, I can basically replace mathematical theorems or examples, counterexamples, by trying to navigate someone through the maze or play a game, which is exactly this kind of path from A to B. And AI is extremely good at this. So many things in modern AI are fueled by what's called reinforcement learning. This is an area of machine learning that makes our LLM foundational models robust through pre-training, alignment, post-training. And even on its own right, reinforcement learning can perform really well even without large language models or foundational models. So in AI research, reinforcement learning plays the role of this rigorous mathematician, if you wish, or some kind of judge that tells all these AI models to stay on course and do the right thing. And the way it does it is via interaction with environment. You can think of autonomous vehicle or some kind of robot or AI system trying to find steps for logical steps for mathematical proof. And in all of these cases, what happens is that by making right and wrong choices, it learns what to do and what not to do. Kind of like us. So we try, we fail, and we learn from those experiences. So since my goal is to talk about algorithms, I'll start in the beginning. In modern day AI research, one of the first algorithms was called DQN, that stands for Deep Q Network, and that was introduced by DeepMind in 2013. So the paper in Nature was published in 2015, but now this is really the most basic AI algorithm that we teach in reinforcement learning courses, AI courses. It's almost like Honda Civic. It's very basic, runs really well, only 100 lines of code, very, very easy to work with. And that's actually an interesting story how it started, because now we look at it as something very basic and primitive, but back then, this was actually one of the very first accomplishments of Google DeepMind, or DeepMind at the time. It wasn't actually merged with Google yet. So there is a movie about Demis Hassabis and DeepMind, how things started, and it shows that the journey to this algorithm wasn't easy at all. So they tried to play Atari games. It was way before chess games and other board games at the time. And they tried to build AI system which would succeed on Atari games. And they failed most of the time, and they were frustrated. The movie actually shows even this part. It's typical research, and then they finally found something that works. And that was the beginning of this modern era. Since then, many new algorithms were developed, and there is still a lot of work to be done here. And that's exactly what this talk is about. And I want to emphasize that for the superhuman mathematical reasoning that we are trying to build, many others in Silicon Valley are trying to build, there is a lot of work needs to be done, but this is roughly the starting point. I already mentioned that there is a difference between easy math theorems and hard math theorems. And similarly here, people from the beginning realized that there are easy games and hard games. For instance, when we were celebrating, or the world was celebrating, everybody focused on the upper part of this diagram, which shows performance of this algorithm on different types of Atari games. So most of them, algorithm did really well above the human level, which is this line in the middle of the slide. But on some games, it didn't do so well. And there was one game in particular which got exactly 0 score. So it means that algorithm miserably failed. It never managed to get even a single point in playing this game. So this attracted attention of AI researchers. And again, this was 2013. So for the next 10 years, this game, that's called Montezuma's Revenge. To me, this means really nothing, except that now it became an obsession in reinforcement learning community. So then, since 2013 onward, this became kind of a challenge. And many teams try to invent new algorithms, do better on this particular game. Again, it was just a goal of trying to teach AI to play Atari games. And it was an interesting time, even though we're talking about ancient time by AI standards, more than 10 years ago or about 10 years ago. And even though we're talking about Atari games, it actually is interesting that some dots on this plot which show the progress were beginning of whole new branches in reinforcement learning and AI development. For example, C51 here, 51 is a very esoteric thing because it stands for a number of beans in the particular algorithm that this team built, so it means actually nothing important. But the C51 is a beginning of what's called distributional reinforcement learning, so that's a whole new branch that then became kind of thing of its own, and so on. So many interesting ideas and things that we use today were introduced during that time, and people started inventing more and more algorithms because they realized that what one is missing in this particular game is some level of exploration, that the system is not exploring it enough or does not have enough curiosity of what it means to learn and develop outside of the box, okay? And this is challenging. So again, many teams have tried. They're very smart people. And this illustrates papers that have been published, meaning that they considered it as a success, but you can imagine how many unsuccessful attempts people have made during that time. And then finally, around 2019, there was this work called Go Explore. As the name suggests, it actually managed to resolve this exploration challenge and did it quite well, so that now we went not just above the human average performance on this esoteric game, but above the human expert performance. So we can call it superhuman ability on this particularly challenging exploration game, which is, again, still just an Atari game. So I want to compare this plot. I'll come back to games in a second. But I want to compare that plot of progress over almost 10 years, so it was a very long time by AI standards, to something that's happening right now. So a couple of years ago, that same company, Epoch AI, that I mentioned earlier, it also started doing studies on AI models performing mathematical reasoning at various levels, some of the levels I mentioned in the beginning of the talk, including the most challenging technical level of human experts. So there was a particular benchmark produced by expert mathematicians that contains problems not at the graduate student level, much, much higher, something that if solved would definitely merit a really good paper in mathematics. And I personally was responsible for geometry and topology section of this particular study and benchmarking. And I was convinced that it would take many years until about 15 problems in my section would be solved. And it's true that my section luckily stood the test of time probably longer than number theory and other areas of mathematics. But many of us were surprised that by now, which is spring 2026, we are approaching 50%. So 50% of those challenging problems fell. So that tracks the progress. And also, I want to kind of compare this curve, which starts very low and slow, and then gradually goes up, and it requires many, many iterations of smart people producing better algorithms, better AI systems. So it's a hard work, and non-trivial progress, it's not a straight shot. So we don't know where to go. We have to, in AI research, explore many systems before we finally find something that works. So very much like this previous slide I mentioned here. All right, going back to games and thinking about mathematics as a game, you could probably say, Sergei, we're already in 2019. Isn't it this time when AlphaGo and all other exciting things are happening? And yes, it is already that time. So AlphaGo did spectacularly. That's another success of DeepMind on board games. But a lot went into that system, including our human expertise. So what we learned as human actually was part of the design of the system. And then DeepMind did the right thing, so they tried to eliminate all these injections of human expert knowledge into the system, eventually reaching the level of a system called mu0. So it progressed from AlphaGo to AlphaGo 0 to Alpha0, and finally what's called mu0. That's a system that doesn't even need to know the rules of the game. By seeing and playing and receiving rewards, it learns what the rules are, and that seems super spectacular. So how do you think this performed on Montezuma's Revenge? So on this plot, this mu0 is a point I. Okay? So it performed just as badly as this original algorithm DQN. So again, this shows that it's a non-trivial thing, that for certain tasks, some algorithms work and they're really good. For other tasks, they don't. And this is another line of research where, starting with DQN in that original work of DeepMind, it progressed through many stages, and here there are many other words and algorithms that were invented along the way. Some of the readable words, which are not acronyms, indicate exploration, which is a very crucial part, and many other elements, which go into this kind of curiosity-driven research for AI systems. Now, as I'm talking about board games, I want to point out, so why it didn't work. So what's wrong here? So mu0 sounds such an amazing improvement over AlphaZero. So what's wrong? And there are many things I could say about it, but to explain some of the basic ideas, board games, even though they seem challenging to us, they're actually not that challenging. So typical game of chess lasts only 30, 40 moves. And the longest game of chess lasts about 300 moves. So not only it's a short game, again, think about replacing each step, each move in a game of chess by logical step in a theorem. So we're talking about very simple theorems in that parallel, right? So not only average thing is very short, but even the difference between extreme case and average case is very small. 30 versus 300, so it's only one order of magnitude. Whereas what we need in research-level mathematics at superhuman-level reasoning, and in many other tasks in autonomous transportation and robotics, is where we perform on a long horizon, where the number of steps is not 30, 40. You don't want a robot which can reliably make only 30 steps, or maybe fall half the time, right? You need a robot which will go 30 million steps and never falls. So that's really the challenge we're talking about here. So this is exactly what happens in this really difficult math problems like Riemann hypothesis and so on. We have, like I said, many of these problems are really of the type go from A to B. And in many cases, path from A to B is relatively simple and short, but sometimes in the sea of all possible choices, it happens that interesting cases take suddenly super exponential number of steps to reach from A to B. Okay? And literally, many problems that our lab has worked on are exactly of this type. So question is, how on earth can AI system find this needle in a haystack? How can it recognize that in the sea of average cases, there are these super challenging, very distinct other cases? So therefore, this is really about AI recognizing how in data to spot needle in a haystack, or equivalently, play very, very long horizon games. It's very much like playing a game of chess on a huge board, which is not 8 by 8, but rather million by million. And this is what it's about. The difference here is that in Atari games, in chess board games, what happens is that if you're on the wrong path, you very quickly learn what not to do. So this is exactly what our parents tell us: learn to fail early or quickly. And for short games, that's exactly right. That's why these type of games or tasks or problems would be easy to AI systems. But something that requires much, much longer horizon and still be robust and reliable, that's actually still a challenge. That's exactly our job. So after this talk, I'm going to roll up my sleeves and go back to lab and work exactly on solving this issue. So it remains unsolved. Related to it, it's slightly different, but closely related, is an issue that many foundational models, LLMs, and similarly reinforcement learning systems, they do well in roughly the span of the training data. So they become amazing parrots, and they can do generalizations roughly within the span of what they have seen before. But it is this, what's called theory building, going way outside of the box, not just epsilon away, but really miles away, that becomes more of a challenge. So technical name for this is out-of-distribution generalization problem. Again, this is something that's not solved. Many smart people, including us, are working on this. And it's absolutely crucial for this mathematical research that I mentioned earlier, because we are running out of training data. Even though we may have lots of problems from textbooks for elementary school or undergraduate level math, we don't have good examples of proofs of Riemann hypothesis. So a system, there is no chance that it can learn from examples. So it has to build those new steps, the new theory, new definitions, all on its own. So it should be able to generalize outside of the box. And currently, it doesn't do so well. It can generalize a little bit, but not much. So here on this curve, I illustrate exactly the same point from a different perspective that I already mentioned earlier, that in problems that are challenging, often what happens is the difference between average case and extreme case. And all hard, really hard level math, like Riemann hypothesis and so on, they really try to say something meaningful, mathematically meaningful, about phenomena very far in the tail of distribution. So the question is, how can AI go away from generic thing, from regression to the mean, to recognizing such unicorn phenomena very far in the tail of distribution? So I want to leave enough time for questions and conclude with a quote of famous mathematician Vladimir Arnold, who said, "Mathematics is the part of physics where experiments are cheap." And probably he was referring or making comparison to something like building huge colliders or telescopes in space. That's what we have to do in physics to study the universe. In mathematics, we used to need just paper and pencil. But what I try to explain in this talk is that we are very far in AI from solving math, as it's sometimes said. And what we really need is build new AI systems which are very good at generalization, at spotting needle in a haystack, black swan, that's a term commonly used now in financial markets, which stands for something that's very rare but has disproportionate reward. And that's exactly the case with the Riemann hypothesis. Finding solution to any high-level math problem is hard, and it's very isolated needle in a haystack, but to us mathematicians, the reward is disproportionately high once we solve it. So therefore, trying to do mathematics through AI will require building this new AI systems. But the challenge and task that we're trying to address, of course, is not limited to just mathematics. This generalization, theory building, needle in a haystack, and black swans, of course, they occur in financial markets, extreme weather phenomena. There are many other domains, including those I mentioned, like robotics, autonomous transportation, and others, where same challenge is a bottleneck of the current development, current research. So therefore, mathematics is simply cheap environment to do exactly the same research, address the same challenges without the need for proprietary data or expensive data. So with that, I thank you for your attention, and I'll be happy to answer questions.
Thank you, Professor Gukov. Questions are coming from the audience. A popular one is from Cesar Bocanegra. I think we've all been thinking this. My son, who is starting 6th grade this fall, wants to become a mathematician, just like you. What advice can you give him based on his age, 11 years old, and grade level?
My son is slightly younger.
How old is your son?
He's just turned 9, and I'm afraid to give parenting advice because I'm not sure I'm doing a super good job myself. Yeah, in fact, I would love to receive advice.
And you don't ask AI to do that?
I don't ask AI. I think if there is, yeah, so jokes aside, maybe, right, so this is very complicated, but I think it's good to get starting playing with the systems. So one has to be, of course, there are many, it's Pandora's box. So there are many issues here, but I think starting to get some experiences is a good idea. The question how is a very different question. So that I'll try not to comment.
Okay, fair enough. From Anonymous, how does one select training data for solving mathematical proofs? How does training enable and limit progress?
Yeah, so this is a very good question. Thank you. And I want to kind of follow on the point I made during the talk that in passing, but I think that's exactly what the question is alluding to. So in many other domains, for example, if you're trying to build autonomous vehicle, like the one you may see around UCLA, for instance, then training data is collected through real physical world experience where Waymo navigates the streets and records videos and they need to be analyzed. So this is expensive. It involves other engineering challenges and steps that need to be done. In mathematics, it's extremely easy and cheap. So that was precisely my point. That's why I try to paraphrase Vladimir Arnold. Mathematics, it's just operating with symbols and formulae. And when things check out, when right-hand side equals the left-hand side, we're done. So it's very easy to verify. So mathematics provides this very cheap environment where, first of all, data can be generated synthetically if they need be, and also because it doesn't really interact with physical world, performing this reinforcement learning self-play cycle, it does not require going outside of just operation with symbols. And maybe that's another aspect I should emphasize, self-play. So many of the systems these days, they learn through just self-play. They don't need much of human guidance or interaction.
Interesting. Okay. Next, is AI hallucination in math fundamentally easier to solve than in natural language or other areas since proofs are mechanically verifiable?
Yeah, so again, thank you. That's a perfect sequence of questions. So proofs being mechanically verifiable is exactly the answer to the previous question. So now to answer this one, many people, including myself and many labs in Silicon Valley, believe that mathematics is the right step precisely for this reason, to address hallucination or learn how to address it. Because in math, this verifiability, how easy it is to turn this reinforcement learning self-play cycle into very verifiable, robust loop provides basically foot on the door to understanding hallucination. So the problem is actually still the same, but the mathematics provides a better opportunity to learn how to address it in a more controlled setting. But problem is essentially, it's qualitatively, there is no difference.
If AI is incorrect, is the problem from data or the AI algorithm or a combination? If it is a combination, what % is from data and what % is from an algorithm problem?
That depends on use cases. In some instances, it's data. In mathematics, the standard approach is to formulate the problem in such a way that data is not needed. In a sense, it's machine learning to do self-play, how to go from A to B, or play certain mathematical game. For example, many problems in group theory are very much like Rubik's Cube. So group theory is an area of mathematics about symmetries, and Rubik's Cube is a basic example of it. So we can think of many of the systems as trying to solve Rubik's Cube of size 50 by 50 in 100 dimensions, for instance. So that's literally what mathematics is. It doesn't need data. It can be done in self-play mode. So in that sense, in math, most of the time, problems have to do with, not with data, but with the other two pillars that I mentioned in the beginning, which are either compute, which we can scale, at least to the ability we can right now, and algorithms. So that's why in this talk I emphasized algorithms, because this is something that we can really control. It's a new area of research which is largely unexplored, uncharted. It's been only a few years that many smart people in the world have been exploring this new domain, and there is a lot to be discovered in this particular area.
And final question. Are there any AI models that have taste, i.e. are able to identify which problems truly matter? Or is it just what humans point it towards?
This is an excellent question, and it's brought up a number of times in many AI conferences and meetings. And at this point, the answer is that there is nearly nothing that can indicate taste. And that's an issue, because imagine that, and this may be a possibility, that a few years from now we'll have a machine that can generate billions of proofs, all of which are worthy publications in top-tier journals. So how are we going to handle that? And shall we select better or worse? And nobody knows an answer to this question. That's a very good question to start thinking about, or maybe we're already too late. We should have started thinking about it a while back. Yeah, so I think that's a good question. Another aspect of it is currently we have some, at least in mathematics, some benchmarks that we developed and guide us based on taste. For example, problems I mentioned, such as Riemann hypothesis, Hodge conjecture, which are part of Millennium Prize problems, they serve as North Star for young researchers in mathematics. And even though graduate students work on much smaller problems, they usually are motivated by addressing these big challenges. And those challenges are set based on the culture of math community over centuries and serve us as beacons to where to go. But if imagine a world where most of these problems are solved, then we lose our beacons, we lose our guiding stars. So I don't know. That's a very good question. I don't think anybody has a good idea.
Very good questions, very interesting answers. We are actually out of time. So, but I'm sure you'll be here if you want to come to the stage and say something. That's all right. Thank you very much. And I think the answer to Caesar, your son, probably should not be playing Atari Montezuma revenge games. I think thank you. A big hand so much for Sergei Gukov. He's amazing. Wonderful. Thank you. Welcome back, techers. Please take your seats as we get ready for our next seminar. Welcome back from AI to American politics. That's a transition I would not have predicted when I graduated in 1983. Fellow 1983 people here? 1984. Yay, 1984, here for, okay, all right. But here we are, and welcome back to campus in 2026. Our next speaker is Jonathan N. Katz, the K. Sugihara Professor of Social Sciences and Statistics and a former chair of the HSS Division. He's also a fellow of the American Academy of Arts and Sciences and an inaugural fellow of the Society for Political Methodology. Jonathan builds statistical models for social sciences with a particular focus on elections, how to measure partisan bias, incumbency advantage, and responsiveness in U.S. legislative races. So no matter what side of the aisle or middle aisle or end aisle you are here in Beckman Auditorium, as you take your seats, and thank you very much, fascinating science is ahead. Please, if you will, give a warm, loud 10 a.m. welcome to Professor Jonathan Katz. And cheers.
Thank you so much.
All right, sir.
Class of 86 not here, but so thank you. So yes, this is a little bit of a change from the previous talk, but not as big as you would expect. In fact, most of my day job is building pretty complicated, pretty computationally expensive models, but my domain of interest, unlike the previous speaker, was mathematics. Mine is in mostly the study of politics. Okay. So my work sits at the intersection of economics, political science, and economics. I have been on, my work, political methodology, which was mentioned at this thing, that's a term you probably have never heard of, don't worry. It just means, that's the word we use for talking about building statistical models in political science. In economics, if any of you took economics classes when you're here, it's called econometrics. In other fields, it's statistics, all the same thing, mostly, just different vocabulary. So about half my work is developing statistical tools, which is mostly what I'm going to talk about today. Trust me, very limited math, hopefully interesting. So, but the other half is actually then doing quantitative analyses, mostly with political data, but I do work with financial data, health data, you name it. I'm sort of a jack of all trades. A lot of research gets chastised, particularly in the social sciences, for like being a bit of navel gazing. The work I do, I like to think has applications. I've been involved in more than 50 election law cases, of which 4 have been ultimately decided by the US Supreme Court. For those of you worried about partisanship, I view my job, as this talk suggests, about science. I work for both Democrats and Republicans. My job is to analyze data. The lawyers' jobs are to spin it. I've also advised startup companies and financial companies where the types of stuff that I do actually really matter, like money is made and lost. Scarily, I've been on the faculty since 1995 with a little hiatus when my wife and I were trying to solve our joint career issues, where I joined the University of Chicago, where Tom, who's sitting here, was previously. This work that I'm going to talk about today is based on work with Gary King. Gary King is a professor at Harvard. He was actually my postdoc advisor way back in the day. And Danny Ebanks, who's a former grad student of mine here at Caltech, who is now a research scientist at Harvard. Right, and so really what I want to convince you of today is that a sort of science of politics is possible. That is, we can talk about generalizations. Now, I like to, and this is, I should say, a hallmark of the social sciences at Caltech. We really anchor the sort of science end of the social sciences. And it's a really hard task. I like to joke with my chemistry and physics that they have it way easier. My objects of study have free will. Right? Right? That just makes the world way more difficult. Okay. So, what do we mean by science in general? And I'm not going to get into a whole philosophy of science talk, so don't worry about that. But roughly means we can make generalizations that apply in different contexts, right? If you tell me something about the conditions, I can tell you something, what's the predicted outcome, with some levels of guarantees, right? So it shouldn't matter what year of an election I'm looking at, what chamber I'm looking at, and I'm going to show you examples that the sort of same statistical models are going to fit the US House and the US Senate. Right, across states, I'm not going to present any evidence of today, across decades. Right, so really, a lot of, so we're not interested in explaining one election. That's in some sense easy, right? In fact, it's too easy, right? I want to explain all elections, right? This is a really hard test case for statistical models and theoretical models in social sciences. Why? Well, we got lots of data, right? Lots of variability. And by the way, and everyone's an armchair student of politics, right? I actually never say when I get on an airplane that I'm a political scientist, ever. I say I'm a statistician, which is true, at least 50% of me, right? Because everyone seems to have an opinion. Right, so we're going to look for these enduring patterns. Oh, good, it's working. So I just put on the left a little slideshow of random books. Literally, this was about a 10-minute Google search of books that people write about various elections. So literally, after every election, people write books about what happened. I get asked, the president's office, alumni groups say, Jonathan, we just had an election. Come tell us what happened. And I'm happy to do so. And it's not that these things aren't important, right? They're datum, right? They're the stylized facts we use to build models, but they're not science, right? Right, the scientific question, again, to reiterate, is what's the generalization, what's the regularities that survive across time? Right, so ultimately, right, for science, I need you to be able to verify, or more importantly, falsify my claims, right? Which is something you probably don't think about when you think about politics, right? Politics is very emotional, right? Right, so the goal is to move from one election stories to claims that can be checked, revised, and reused. So this is where the title for this talk came from, although I changed it in my title slide. What Gary and I and others are interested in are these empirically verified universals. That is, things that happen regularly, I expect to see, I've seen in past elections, I expect to see in future elections. Or you might want to think about it, the thought experiment, if I were to set up the same rules again and run the election the exact same way, I would expect to get the same types of results. Right? The evidence standard is travel across elections, chambers, and personalities. Something I'm going to spend a long time on is a word which has now gotten in vogue because we talk about generative models, AI. But it's the same sort of sense. We're talking about generative accuracy, which I'm going to come back to in a second. Right? And in fact, I'm going to show you that the models that we fit today, almost everything we know about legislative elections comes from studying the US House of Representatives. Why?
It's big.
It's big. There are 435 districts, right? For those of you who took Math 3 or its equivalent, right? I can run a regression. I got 435 data points. I can get pretty reasonable estimates of things. Great. I want to study the US Senate. Got a problem. Right? Yeah, there's 100 senators, but only a third of them up every election. Right? I'm going to show you that the same model is going to fit the House and the Senate data. By the way, the results I'm going to show you about the Senate, no one systematically studies the Senate. All right, so what are universals? Instead of a formal definition, I want to give you examples. The first one, which was talked about in the introduction and is now all the rage as we talk about the redistricting wars going on, is that election rules matter, right? If you let me draw districts in particular ways, I can skew the results in favor of one party or another. Political scientists, we call that partisan bias. Responsive, you probably haven't heard of. That's sort of basically how much does a 1% change in vote change my seat share? Right? Another one you probably never heard of, and I even put the name down, is priority rule pushes towards competitive two parties in a district. This is known as Duverger's law, named after Maurice Duverger, a 1950s French sociologist and lawyer. And this work has a tight relationship to Caltech, so that's why I'm going to give a little aside. One of my co-advisors in graduate school was Gary Cox. Gary was both an undergraduate at Caltech and a PhD in social sciences, early PhD in social sciences at Caltech. And he wrote a whole book called Making Votes Count, showing that this claim that Duverger made, and some others, basically travels across all advanced industrialized countries over a very large time swath. And it really impacted me. I was an RA on this project when I was in graduate school. Another thing which you probably don't think about is we think elections is really chaotic. But actually, they're really predictable, which is oddly scary. So suppose I wanted to predict next year's election. Turns out that, well, I can't predict next year's. If I could do that, you know, I go on Cauchy or like and make a lot of money. But so what the point level is difficult. I can tell you that the election results in any given district basically swing uniformly. What does that mean? So it says that, suppose that the election results go from the Democrats getting, say, 48% of the vote on average in the previous election, and this election they got 52%. So they got a 4 percentage point swing in their favor. If I wanted to predict the election outcome in each and every district, my best guess is a 4% swing this uniform swing. So that's a really simple idea. You just think it should never work at all. It has an error rate of about 0.01 percentage points. Yeah, crazy. All you people, all you independent agents making decisions, you make really predictable decisions. Why is that? Well, not surprisingly, you're being impacted by similar information flows, by the state of the economy, right? And there's other features that are going to drive you to making similar decisions on average. Again, any one of you, I can't predict any one of your behaviors, right? That's the free will problem. But on average, a large set of you, we're good at that. Okay. Surprises have structures. So one of the reasons why the Republicans are very concerned right now, besides the fact that Trump is particularly unpopular, is that in general, the incumbent presidential party does poorly in the midterm election. For a pretty simple reason, it's called thermostatic politics, right? We elected one group, maybe went too far, so let's try to dial it back, right? Right? And I'm not going to show you everything, but we've checked these patterns over roughly 2/3 of a century in US elections. So essentially what I want to build is an instrument. My instrument's a statistical model that tries to identify these consistent patterns. Right? It's going to make visible these otherwise hidden things, right? Now, some of these things I didn't need a model to do. That the president's party does poorly in midterm elections, that's like any pundit worth his salt will tell you that, right? There's more subtle things we can look at that get found out by using a good model, right? And so really what I do for a living, and what this talks about, is about building this instrument. Okay. All right. So if any of you took Math 3 or its equivalent, or a basic stats course, right, you learned about uncertainty. And the uncertainty you learned about was sampling uncertainty. Why did you learn about sampling uncertainty? You learned about sampling uncertainty for a couple of reasons. In the early 1900s, when the sort of modern basis for statistics was being developed, I know it's going to find it hard to believe because we all have, these amazing computers in our pockets. Getting data was really hard. So data sets and experiments were small, right? In the world of small experiments, sampling uncertainty is huge relative to anything else. It's the first order problem. And also not to disparage my mathematical statistics friends, it's also the easiest way to use to generate theoretical results about uncertainty, right? Because we get to invoke both the laws of large numbers and central limit theorems, which tells us something about this, right? What's the problem we live in today? This was sort of, in part, a discussion of the previous talk, right? Data is now ubiquitous. I can get data together really easily. Like data sets of 10, I work with small data sets compared to my computer science friends, right? 10,000, 50,000, I have auction data on my computer that's, hundreds of thousands, right? Well, what happens when I have hundreds of thousands? The answer is my sampling uncertainty is essentially 0. Well, that would imply, if I thought this was an accurate measure of my statistical uncertainty, what I don't know, is I wouldn't have any uncertainty. That's false, right? We have lots of stock market data, right? So if sampling uncertainty was all there was in the stock market, we would all be really rich, right? That's just not true. So the key in the world where we have medium to large size data sets is not sampling uncertainty. It's what I like to refer to as systemic uncertainty, right? And really, that's just an acknowledgement that there's lots of things not in my model. It could be because I don't know them. It could be because you're all, again, have that nasty free will thing that makes my life so difficult, right? Right? But if we don't account for the systemic uncertainty correctly, I make really poor inferences. Or in better terms, I make really poor decisions. Right? So how we fix this requires a different mindset, a different set of tools than we used to use in statistics. So before getting any results, I want to talk about 4 key principles of modern statistics that I use and are ubiquitous now in statistical models. The first is this idea of generative models, which again has gotten to be all the rage because of AI, but generative model just means that my model fits the data, right? I'm going to be a little more careful about that, although I'm not very. Says that once I fit my model, and ideally when I fit it to out of sample, right, I should get the same sorts of patterns. I should be able to replicate that. How do I get this systematic uncertainty? Well, you were probably taught, if you took a basic statistics class, that keep it simple. We want really simple models, right? So in my field, we talk about models as the number of parameters. Again, a word that you've now become familiar with because every day Anthropic and OpenAI issue a new model, and their models have billions of parameters, right? My models don't have billions of parameters. I have 10,000 data points roughly in my data set. So typically, if you were doing this in a normal world, you'd fit, maybe at most a few hundred parameters. The model I fit today has over 5,000 parameters on 10,000 data points. How can I possibly do that? And the answer is the second bit, which is, so I allow those parameters to potentially be non-zero. Almost all of them are 0. And I'm going to let the data only let the ones that really have clear evidence that they're non-zero end up in my final fit. And this is, again, nothing unique to my modeling. This is a mainstay of machine learning, or in some sense, it is the mainstay of machine learning, right? So this lots of parameters. One way we're going to get more systematic uncertainty. We're also going to use some different distributions. And I'm going to do so in a Bayesian computational model. Don't worry, again, I'm not going to present any of this up. But again, this is something that has advanced that allows us to make what were otherwise intractable models tractable. The Bayesian approach is nice because it lets me easily incorporate systematic uncertainty. That's not just sampling uncertainty. Now, when I was in grad school, or when I was an undergraduate learning about Bayesian statistics was not possible except on toy problems. Why was it not possible? Well, for those you want to remember back to your Math 1 days, to basically solve for a posterior, I have to do integration, right? So, okay, 1 dimension, 2 dimensions, we can do integration. We can do numerical integration, not so bad. Now I want to integrate a 5,000 dimensional thing. The answer is it's hopeless until modern tools came about. And the modern tool that I use all the time is something called Markov chain Monte Carlo, in particular a version of it called Hamiltonian or hybrid Markov Monte Carlo, depending on which branch of you learned it in. I'm not going to go into what that is, but it's going to allow us basically to estimate integrals, to do integration in very high dimensional spaces reasonably efficiently. A lot of this, the other thing that's made this possible is not just advances in the tools, but advances in computation. Right? So this is not possible without modern computing. So the model that I estimated when we did our first models took 3 weeks to run. Now, we've tweaked things and we moved things to GPUs, and so now it takes 4 hours. But it was not possible on the computer I came to Caltech. When I was hired at Caltech in 1995, Caltech was very generous with my startup. I had a HP UX workstation that cost $50,000. It would have 0 chance of estimating this model. Right? Also, just to put this in perspective, the iPhone in my back pocket right now is way more powerful than that $50,000 workstation that Caltech bought me when I got here. Okay. How am I on time? Okay. So we're going to say a model is generally accurate when elections simulated look like the real elections. So this graph on the right here is the non-shaded area is the actual data. So this is just a smooth histogram of the data for 1960s and 2006, right? And the shaded in pink red is model from the data that was, well, I'll call it the normal model. It was actually a model developed by Andrew Gelman, also a longtime collaborator of mine, and Gary King in the early 1990s. And you can see the model is terrible, right? If the model were generally accurate, right, these two sets of curves would overlap, and they don't overlap at all, right? In particular, they do really terribly in the area that we care about, right? In competitive elections. The models predict basically no competitive elections. There actually are competitive elections, right? Now, I didn't choose these years at random. Literally, 1960 is the worst fitting year of the data, and 2006 is literally the best fitting year of the data. So if a student presented data, you should not believe this model. In fact, this picture is what got us all along this rabbit hole that is this research. And it all came about, we're trying to just port the old model that Gelman and King did to a new tool set, which automatically generated diagnostic plots like this, and we said, oh no, that's a problem. Okay, so what do we do? So I told you to get the systemic uncertainty, we need to model it. So we're going to do so by moving to what's called an additive logistic student T. So our vote shares live on 0, 1, or 0 to 100. So fancy terms, that's a simplex. Problem is, there are hardly any distributions on a simplex. Okay, so we do a standard trick in mathematics, which is we move something from the simplex by taking a logistic transformation, which takes something from 0, 1 to the real line. Nice thing about real line, lots of distributions. Particularly the student T. In our case, what the student T is going to allow us to do is it has these fat tails, which is talked about these black swans in the previous talk. But it's also going to concentrate mass in the center for very low degrees of freedom. And remember, if you look at those old pictures, that's where we got problems. I don't have enough mass in the center. We're going to fit a single hierarchical model jointly to both the House and Senate instead of treating them as separate problems. We also use some richer set of predictors in our model, made possible, by the way, by modern agentic coding tools. Adding new variables would have normally taken me years and tens of thousands of dollars of RA time. Me, Danny, and Claude and Codex, we're a great team. I'm not going to talk about it today, but we're also going to worry about how we handle uncontested elections, right? And we're going to use hierarchical things. We're going to use modern computation. So here's my first test of this model. So out of this fit of this model, I can now ask, do the parameters look different between the House and the Senate? And the answer is, so the dot is the point estimate of this difference. So notice that all but 1 are pretty close to 0. All but 2 are pretty close to 0. The dark bar is the 50% confidence interval, and the large bar is the 95% confidence interval. Basically, all the fundamental parameters that drive these elections are the same for the House and the Senate. And the ones that differ, we know why they differ. The one that differs is lag Senate, because, well, think about lags. Lag in the House election is 2 elections ago. Lag in the Senate is 6, so not surprisingly, they have a slightly different structure. And similarly on the lagged House vote. Basically, the same model fits the data in 2 different chambers. No one knew this. In fact, if you ask the average political scientist who studies elections, they would tell you the Senate elections are totally different than the House elections. Why? Senate elections are all about personality. You actually can name Senate candidates. Well, not so much in, right? House candidates, you can't name one. You could barely name your House member. Okay. Here's another fit. So again, this normal model is this old Gelman-King model. Logistic TICC is our model, right? Like most scientists, we like acronyms. I'm not going to worry about defining it. So what this is we're looking at the model, and we're asking it, the model assign probability that a race is marginal. That is, you can think about it as competitive, right? So the horizontal axis is the actual observed frequency in that bin, and the horizontal axis is the model prediction. So if the model is well calibrated, this thing should live along the line. So our model does, normal not so much. Okay, here's it for the Senate. It's even worse because we've got no data. I want to give you some fun actual results. So remember we estimate these candidate effects. So on the left are the top 10 Democrat and Republicans in the House and on the Senate. Remember, we're fitting this model across all time. So these are so I'm not going to worry about the House ones, because unless any of you are political junkies like me, you're not going to recognize most of the House members. Some of these are going to make sense. Joe Manchin, right, classically accepted as the only possible Democrat who could win in West Virginia, not surprisingly way outperforms other Democrats, right, to the tune of about 7 or 8 percentage points. All right, to put that in perspective, most professional politicians would sell their firstborn to guarantee themselves a cushion of 5 or 7%, right? Other ones you probably weren't expecting, Chuck Schumer, who gets derided a lot. He's the current Democratic leader in the Senate. He is famous in New York. I grew up in New York City for being ubiquitous everywhere. He's at every state fair, every county fair, every high school graduation. It's like, does the man have doubles? Right? And then some others you expect. Susan Collins, who's the only Republican currently left in the Senate from the Northeast, does way better than other Republicans. Another one, who's actually now, you can know why he's running for re-election, Charles Grassley, who will be 94 when his term is up. So he's in Iowa. Iowa's a really Republican state, but he does even way better than an average Republican in his state, right? So, all right. The last substantive one I'm going to give you, is election results. So people say, oh, elections seem really uncompetitive in the US. I beg to differ. So the average probability of a House member losing a seat, now we should point out what that means. They could lose it because they actually lose the election, or they could lose it because they choose not to run for re-election. It's about 17 percentage points. So imagine living your life where every year you have a 17% chance of losing your job. That'd be a pretty terrifying world to live in, right? Even in the world, in these out years, it's 7 or 8 percentage points. Would you take a job that didn't pay you $1 bazillion, where every year you had the possibility of losing your job at 8 or 10%? Unless you're really rich at something, which I doubt many of you are, the answer is no. And this is, by the way, what motivates what Dave Mayhew, one of the most famous scholars of American politics, said, that congressmen seem to be running scared. They're running scared for the right reason, because they lose their jobs pretty frequently. Okay. So I want to hope to convince you a little bit there's a science of politics is possible. There's 4 talks, and so even if you don't care about politics, these tools that I'm telling you are ubiquitous now in studying of tabular type data, be it in elections, be it in finance, be it in healthcare. And the same problems appear everywhere. And this sits at Caltech's tradition of theory, data, experiments, computation, is well suited to this sort of scientific approach to politics. And I'm going to leave it there so we have some time for questions.
Thank you so much, Jonathan and Cass. And I have to say that our speakers tend to think that the questions are very good coming from Caltech, and they are, so keep them coming. Okay, so first of all, we're just going to jump right in. Have any of your universals stopped being universal? Anything that held for years but doesn't anymore?
The answer is no, in part because that's how we define universal. But that'd be a really cool thing. I will tell you the closest thing is a result I didn't present you. So one of the biggest findings in studies of congressional elections is that incumbents seem to do better than non-incumbents. In fact, that's called the incumbency advantage, which is poor grammar, but it's how it's defined. When I was in grad school in the 1990s, in the 80s and 90s, was about 8 percentage points. And it's now down to about 2, back to where it was in the 1950s. Now, you could say, so that doesn't look like a universal. Incumbency advantage went up and went down. Well, in some sense, it's because that's not the universal. So what happens is so you might think, in some sense, a politician doesn't care about their vote share. I mean, they'd like more vote than not, but they care about winning. And so what's happened is other parts reacted to this changes in incumbency advantage. And so basically, remember, if you look at those plots of the probability of defeat of an incumbent, they remain basically fixed over the entire period. So in some sense, I do the classic statistics problem, I'm going to redefine the problem. So incumbency advantage is not a fundamental, but this question about probability of defeat does seem to be one.
Thank you so much. And my question that I was going to ask just went away. If plurality, but here's another. If plurality pushes towards two parties, why do other countries like Germany have more than two?
Very good question.
See?
And something, was that a ringer? Because someone should know that my wife is German, and I spent a lot of time in Germany. So it is the case that Germany has single-member districts, but they actually what's called, in political science, a hybrid system. So there are district-level elections, and so you win, and whoever wins the majority vote in that Bund, in that district, wins. But they also have a proportional representation system, what's called a compensatory system. So suppose the Greens. The Green candidate is never the winner of the two-party candidate, never the majority winner in any district in Germany, yet they have seats in parliament. How do they get so? Because they win on average out 5% of the vote. Why? So they get these seats otherwise. So it is the case that there are district-level elections. The overall effect is really a proportional representation one, so that's why they don't get two parties. That's why the Greens continue to exist, and they have a very hard time in the US.
In court cases you've been involved with, what's the hardest statistical concept to communicate to a jury or judge?
I have to say, luckily, all my trials are bench trials, which is hard enough. I couldn't imagine trying to explain basic statistics to a jury. That said, judges are only slightly better. The answer is the notion of statistical uncertainty is really hard for the average person to get. I usually fall back on betting metaphors, right? So for example, as part of this analysis, we'll say, oh, the expected value, the average value across our predictions is that this seat should get like 52% Democratic vote share, right? So people like lawyers, oh, that's a Democratic seat, or the judge, and I'm like, well, Your Honor, will you bet me $1,000 that the Democrat's going to win? That's how you try it. But how do you think about uncertainty is very difficult for people who don't spend their days worrying about it to understand.
Here we go. And a question from Eduardo Kutelenk. I have to say thank you for coming. Many years your questions have been shared, so we love that. Question is, how do you account for data drift that may affect your outcomes and predictions when using your data for predictive purposes?
That's a good question, right? So this goes to sort of I guess I have to be clear about what you mean by data drift. So data could drift because there's been a sort of fundamental structural break in the underlying data generating process, right? That would be bad. That would show up in my generative checks. Data could be bad because I made assumptions in my data pipeline about how I put data together, and those assumptions change. If any of you ever work in production, this happens, right? Someone changed how they're collecting the data, right? In my world, think about things like surveys. Someone changes the slight word in the question, that changes the data. The answer is you hope you have checks in place to make sure you catch those types of changes, but they're a problem. They're part of why you hire people like me. So both are really good questions. Both are really good possibilities.
Let's try Rob Williamson. How many of those 5,000 parameters end up non-zero?
That's a good question. My bet is a couple of hundred.
All right. Erdny Sangatsyev, apologies if I've murdered your name, as an expert, how you knew these were coming, how would you change the current election system if you would want to in the first place?
So I told you that my view of being an expert witness in court is I'm a scientist. I analyze data and tell people what's the outcome under the current rules. I do worry a little bit that if you wanted to change things, that involves lots of ethical and moral reasoning about what you think a good outcome is and how things should work. So that's a much harder question. What I would like, though, to people think about redistricting, and so one of the concerns right now is sort of partisan gerrymandering, which the courts have the Supreme Court has now ruled basically states are free to draw maps how they like. And the solution has been, for example, in states like California, is to have citizen commissions draw maps. I don't actually love that solution. because that says that somehow if uninformed people do it, they somehow they don't make unintentional mistakes that lead to biases in certain ways. Since we can actually measure biases in very reasonable ways, I'd rather them say like they do for malapportionment that says, here's a standard. The bias can be no more than X percentage points. That's how we handled malapportionment back in the 1960s. So a district that is more than 1% deviation from sort of ideal population is not allowed. It's a clear rule. We can implement it. There's little ambiguity. So that's what I would want clear, unambiguous rules.
And you can run on that. That you can't. That's too long to tweet, but that's okay.
Sorry.
And very hugely popular question: do you foresee predictive markets influencing election outcomes in the future?
Yeah, unfortunately, I do. I think the way we see it, I don't know about what sports you follow or don't. So I'm a tennis fan, and one of the problems in tennis is very low-ranked players make very little money. And so there's been lots of race fixing. So I'm not worried about prediction markets affecting who's going to win a congressional seat or who's going to win president. But you could think about people intentionally or not throwing races because there's been influenced or bought off at very low-level elections. So I worry a little bit about that.
Fantastic. Well, there are many more questions, but we're out of time. So thank you, Professor Jonathan N. Katz. A big hand for this fascinating
Thank you so much.
Welcome back, Techers. In our last session next session before lunch, please take your seats. We're now moving from political behavior to molecular behavior, specifically to one of matter's strangest properties, quantum coherence. Our next speaker is Ryan Hadt, professor of chemistry. His lab looks inside molecules to study how electrons and spins move, interact, and briefly coordinate. Basically, the hidden choreography that determines what chemicals do. That work has implications for solar energy, new materials, and future quantum technologies. Ryan trained at the University of Minnesota Duluth and Stanford with postdoctoral stints at Harvard and Argonne, and he's a Sloan Research Fellow. So you take your seats. Please welcome a warm pre-noon welcome to Professor Ryan Hadt.
Excellent. Thanks so much for that introduction. I really appreciate the opportunity to be here today to tell you about a question that my group is working on. How do we use quantum coherence as a new chemical observable? So many would say that we're living in a second quantum revolution, where the first was the development of quantum mechanics, which gave us things like the laser, the transistor. But the second quantum revolution is the development of additional new technologies by controlling certain quantum phenomena, such as superposition, decoherence, and entanglement. And whether you come at this field as a chemist, a biologist, a physicist, or a material scientist, it might look quite different. But in general, this quantum information science area is broken up into three different subfields. Computing, where we can think about quantum bits or qubits and how we can use quantum computing to generate computational advantages. And in communication, thinking about generating and using quantum information to enhance data security and transfer. And in quantum sensing, thinking about quantum sensors, the development of quantum sensors, and something we'll talk more about today, the possibility to revolutionize new imaging technologies to study how chemical and biological systems operate at the nanoscale and in real time. So first things first, we have to actually generate these quantum bits or these qubits. So this is the fundamental unit of quantum information. Right, the classical bits that our classical computers work off of can take on discrete states of zeros and ones, on and off, whereas a quantum bit or a qubit is really a mathematical object, but it represents a superposition of those on and off states. So you can take on values anywhere essentially on what we call this block sphere. So we have to first physically realize qubits, and we'll talk about that today, how we do that with molecules, actually with unpaired electrons. But then just like in classical information, quantum information will also have certain properties. So classical information, thankfully, in your computers, does not just suddenly erase itself, right? Because it's interacting with its environment. But that's not the case for quantum information. Quantum information has a finite lifetime because the quantum system is so sensitive that it interacts with things in the environment. And so quantum information has a finite lifetime and can be destroyed by interacting with the environment through a decay of this superposition state via something that we call decoherence. Okay? So decoherence is bad for quantum computing and certain quantum information communication applications. However, that exquisite sensitivity to the environment can also be leveraged for certain types of sensing applications. And so we're going to talk about those sensing applications today and how we can use molecules to do this. So coherence, right, you can kind of think of this as a set of synchronized waves, essentially. We have molecular electron spins that we generate coherent superpositions of, and their wave-like properties can add together to give you coherence, and then the coherent states can interact with some, say, noisy environment, and then lose the coherence through decoherence. So again, that could be bad if you want to build a quantum computer, but decoherence really in a molecule is its way of reporting of its surroundings. Essentially, this decoherence is the chemical observable. And I like this analogy to magnetic resonance imaging, right? So MRI is a technique that uses nuclear spins. So MRI transforms nuclear spin relaxation from a bulk spectroscopic observable into something that gives you spatial contrast. So it can give us these images that we see today. Many of us may have had MRIs, for example. And the relaxation time of the nuclear spins in our bodies, for example, in tissue, can vary due to the nature of the tissue lattice, molecular crowding, as well as tumbling and diffusion. So we have a mechanism-based spatial contrast with MRI. In MRI, right, we're using nuclear spins, oftentimes of water and contrast agents. The tissue environment changes the relaxation, and the relaxation, the differences in relaxation becomes an image contrast. Whereas in molecular quantum sensing or molecular quantum imaging, we use molecular electron spins. The chemical environment will now change the coherence time, and the coherence is what we are seeking to develop as a spatial contrast agent. So it might look something like this. We're going to talk about how we do this right now with all optical laser pulses. So we might have this technology does not exist yet. It's something that our laboratory is trying to develop right now. Sort of like a microscope where we can scan a sample, raster a sample, and actually study processes, say in neurobiology, look at interfaces of electrocatalytic energy storage systems, look at membrane dynamics, and do this with ultra-fast temporal resolution with diffraction-limited spatial resolution as well. So this is where we want to go, but first we have to figure out how to generate and detect electron spin coherences on molecules, and we need to understand what the decoherence rates are actually telling us about the molecular chemical environment, right? So that is thinking about, that's fundamental science, thinking about decoherence mechanisms. That's something our group is really interested in studying, and we do a lot of that work, and we'll see how the ability to all optically generate and probe coherences on the ultra-fast timescale has led to really new science. So molecules are not the only way to generate qubits, right? There are other technologies to do this, things like the superconducting loop, trapped ions and atoms. And these are actually, especially the superconducting loops, which are popular for quantum computing technologies, are kind of large physical objects, right? And you also will notice that the temperature at which these qubits operate below 1 Kelvin, right? So no way we're going to use these technologies for quantum sensing in real chemical biological systems. But I do want to point out these so-called diamond nitrogen vacancies, where you have a diamond lattice and you have a nitrogen impurity, and next door to that you have a vacancy center and you have unpaired electrons sitting at this nitrogen vacancy. And those unpaired electrons can be made to be coherent and can be studied at room temperature. You can see here. And this has led to a number of really interesting quantum sensing applications already, very powerful technology. So atomic imaging, nanoscale thermometry, imaging magnetic fields and live bacteria, actually following single neuron action potentials due to really tiny changes in magnetic fields when ions are moving through a system, and also the ability to study condensed matter magnetism at the atomic level. So the question we have is, could molecules, right, become the nitrogen vacancy centers of chemistry? And the answer to that question definitely is yes, especially if we're just interested in molecules that have unpaired electrons on them. There's all sorts of molecules that are paramagnetic, they have unpaired electrons. But this question becomes a lot more nuanced when we think about the nature of generating and detecting coherences. So it's not as simple as just needing a molecule with unpaired electrons like a diamond nitrogen vacancy. And also it's important to point out that diamond nitrogen vacancies have a finite size and distribution, right? We have basically a solid state architecture. It's a diamond lattice of repeating carbon atoms. And that lattice has a fixed geometric and electronic structure, so therefore the coherent electron spins also have their coherence properties fixed by the lattice structure. And they're difficult to surface functionalize and actually get them where you want to go in specific chemical systems. But molecules, right, if we think about synthetic chemistry, we could have synthetic control, atomistic control over the coherence properties of molecular qubits, and we can target their delivery to specific systems to ideally, as we've been talking about, provide spatial and temporal maps of biochemical microenvironments. So 2 key goals that our laboratory has been focused on, firstly, is can we do this all at room temperature, right? Let's go from sub-Kelvin up to room temperature like diamond nitrogen vacancies, right? That's where chemistry and biology happen. And we also want to do this all optically, so we can have systems that are compatible with microscopy, and we want to do this with ultra-fast temporal resolution to take advantage of laser technology. And so this is where we had to develop a missing capability. So one capability to generate and detect electron spin coherences in molecules is electron paramagnetic resonance. Super powerful method, very high resolution method to study electronic structure. However, it requires the use of gated microwaves. So microwaves can, one, limit your spatial resolution and also limit your temporal resolution because of the fundamental time constant that is necessary for using pulse microwaves. So you can't measure coherences shorter than around 100 or so nanoseconds. And then with optically detected magnetic resonance in these nitrogen vacancy centers, microwave technologies are also still needed. And if you try to mimic the electronic structure of a nitrogen vacancy center in a molecule, right, unpaired electrons, say in an example here is a chromium-4 complex, the spin relaxation, the decoherence rate is so fast, you can't measure the decoherence above liquid nitrogen temperatures. So another fundamental limitation there. And so our group has been working on ultra-fast magneto-optical techniques to generate and measure spin coherences in molecules, and we'll talk in some detail about this approach today. But we've already achieved hundreds of femtosecond temporal resolution, and for our applications, really, you don't need to press any farther than that. But this is what we'll talk about, and this is the technique that our laboratory has been trying to pioneer for molecules. And this is fundamentally a new measurement regime. So EPR, nitrogen vacancies, versus our new work. Our work works with molecular systems. It can provide hundreds of nanometer spatial resolution because we're working with visible light, which now you can use the diffraction limit to do microscopy with. Works under ambient conditions, as I'll show, and has an ultra-fast temporal resolution. And so what Erica, a postdoc in my lab, did, she judiciously chose a molecule. I won't get into the judicious nature of this choice during this talk, but it's very interesting in case people want to talk about it in the questions. It's an iridium-4 center surrounded by 6 chloride ligands, and it has an octahedral symmetry. And then what Erica could do is to leverage the differential absorption of left and right-handed circularly polarized light in this compound. So this is circular dichroism measured under an applied magnetic field, and then construct the spectrometer to generate and measure the coherences, where we have an ultra-fast circularly polarized laser pulse excite the sample just in liquid, room temperature, sitting in the room temperature bore of a superconducting magnet, which folks will show you today in our lab if you happen to do a tour. So that excitation generates the spin coherence. The probe then comes in, it's linearly polarized, and you measure the polarization or the ellipticity change of that probe pulse as a function of time, and that measures the electron spin coherences with the ultra-fast temporal resolution. And with this, we can now measure molecular electron spin coherence on the femtosecond timescale at room temperature. So I think it's, many of you probably can grasp the nature of a femtosecond, but right, a femtosecond is to 1 second, as 1 second is to about 32 million years. And so it's a pretty big difference there. And also, as fast as light is, light only travels about maybe 300 nanometers, the size of a bacterium in a femtosecond. So that kind of puts that into perspective. We now have a technique to generate and measure electron spin coherences on molecules at the same time that they're actually moving in solution, the same time with which bonds can be broken and made. So the same time scales that actual chemistry is happening. And so for those of you who like to look at some data, right, we always like to look at data. In fact, my PhD advisor, I like to joke, always says, let the data speak to you, right? So let's see what the data have to say. So here are some ultra-fast magneto-optical data taken at room temperature for this iridium complex, just dissolved in water. So just pretty much as ambient as the conditions can get. You make a measurement at 0 applied magnetic field, you see this exponential decay, but as soon as you start to apply a perpendicular magnetic field, you see these oscillations grow in. These wiggles, these oscillations are actually the electron spin coherences. So these are the superpositions of a single unpaired electron on an iridium-4 center in this iridium chloride complex. And the coherence lasts for about 10 picoseconds. So that's the shortest molecular coherence time that has been measured to date. And you can compare this to the technology, the spectroscopic method that I've talked about previously, electron pair magnetic resonance. You can freeze this sample into an optical glass, and you can put it into an EPR spectrometer, and you can measure the decoherence times, essentially up to about 20 Kelvin, at which point you reach the detection limit of this instrumentation, this technology for this particular molecule. But if you extrapolate those low temperature data out to room temperature, this is the point that we measure with ultra-fast magneto-optics. So this is a 5 order of magnitude increase in temporal resolution for this experiment. So that's pretty significant, and significantly it gets us into this regime of room temperature solutions. We can study these coherences under ambient conditions. And then for you spectroscopic enthusiasts in the room, we can also get something called the G-value backed out from the Larmor precession frequency coming from the magnetic field dependence of these data. And the G-value tells us a lot about the electronic structure of this molecule. So not only do we have a spectroscopic technique to give us coherence, we have a spectroscopic technique that tells us other insights, spectroscopic insights. So we can then couple those to get even further insights. And then we can start to show that indeed the molecular coherences that we measure are sensitive to the chemical environment that the molecule is in, and that the coherence really does encode information about the local chemical environment of this molecule. So the first thing that we did was to just vary the viscosity of the solution of the water by adding a little bit of glycerol, which is a little more viscous, a little thicker solution. And what this does is effectively slow down the rate of the molecule moving and tumbling in solution. And that leads directly, that slowing of the rate of tumbling leads directly to an increase in the time constant of the coherence. So a decrease in the rate of coherence. So we slow down the molecular tumbling, decoherence occurs less quickly, right? And we can also show that our concentration detection limits are also comparable to electron paramagnetic resonance. Again, the sort of the gold standard up to this point for coherence measurements. So I also want to give you a sense for, now that we've been able to do that, where our lab is going in terms of these mechanistic investigations of decoherence and to future applications. One is to think about if we want to image tissue, for example, while we won't have the same penetration depth as magnetic resonance imaging, we could still have a number of applications where we would actually want to get light to penetrate tissue. So we can swap out the chlorides with bromides. So this is an X-ray crystal structure of the iridium bromide complex, again an iridium 4 center. And in doing so, you shift the absorption bands. So this is where this complex absorbs light. You shift it from the UV visible range, so the visible light range, into the near infrared, where the largest tissue penetration depth is for visible to near infrared electromagnetic radiation. And then you can still, with this new molecule, measure the electron spin coherences, just like we could in the iridium chloride. And you can go from water to more viscous solution to actually trying to slow down the tumbling as much as possible by affixing the molecule in space into a thin polymer film. And you can see an order of magnitude increase in the decoherence time when you do that. And by increasing the decoherence time, you also show an increased sensitivity to environmental perturbations. In this case, increased sensitivity to, say, magnetic fields, right? So we're interested in detecting electric fields, magnetic fields, for example. And so this is an example that we like because the same molecular motions that we are studying and detecting in solution are those that destroy the coherence. And also it's the same that become the coherence contrast mechanism, right? So the tumbling rate of the molecule in solution in this case. And then another proof of principle concept that we wanted to develop was to utilize the ability for this molecule, which is actually has a 2- charge, so it's dianionic. And because of electrostatic interactions, it can interact with cations, so positively charged molecules in solution, through ion pairing. So if you think about taking an anionic molecule, cationic molecule, and then ion pair them together in solution, the effective size of that system gets larger, and so that will slow down the tumbling rate of that molecule in solution. And by what we just saw, we should have some sort of quantum sensing ability through those tumbling rates. And the proof of principle that we sought to look at, Juliet and Jake in my group, was to look at the interaction between a neurotransmitter, acetylcholine, which is important for muscle contraction, memory, cognition, is also implicated in Alzheimer's disease, and seeing if we can just detect this in solution with our iridium complex. And indeed we can, and in fact we can detect this molecule with about a concentration of about 10 millimolar. And this is significant because if you look at the neurons that have these vesicles that contain acetylcholine, their concentration of acetylcholine is actually quite large. It's like hundreds of millimolar. So even much more significantly more concentrated than our current detection limit. And then transiently, as neurochemical signals are being passed in the synaptic cleft, it can reach also concentrations of 10 millimolar. So this is, again, a proof of concept that we can use the electrostatic interactions to sense and basically detect the presence, in this case, of a neurotransmitter. But, and just to finish up this, we can also look at the concentration dependence of this interaction and how it affects the decoherence time to back out thermodynamics of this electrostatic interaction in a unique spectroscopic manner. But again, this is just a proof of principle. You know, we're certainly not at the point where, you know, we would actually be able to image a neuron and try to follow acetylcholine dynamics, especially because we're leveraging just the thermodynamic interaction between the electrostatic interaction between these two molecules. You know, this is driven by electrostatics. But the nice thing about chemistry, right, we could say modify this structure to give us a chemical group that might be highly selective in binding specific targets, specific sensing targets, analytes of interest. But in order to do that, we actually need to synthetically change this structure. And I've talked a little bit about the octahedral symmetry of this molecule, and that's actually really important. So we needed a way to be able to change the structure, but still be able to generate and measure the electron spin coherences. And this is something that Jonathan's here today, and Erica, a postdoc in my group, have done. So we have these high symmetry octahedral iridium-4 complexes. What they did is they went to a lower symmetry, so now what we would call more axial symmetry. This is a tungsten, triple bonded to an oxo with 4 other oxygen ligands. So we lower the symmetry, and you know, again, for this mechanistic, the secret sauce, if you will, still this molecule has the ability to interact strongly with, you know, with left versus right-handed circularly polarized light. And so this gives us a way to lower the molecular symmetry and open up the synthetic chemistry space that we can use this technique for. And what they could show is with this tungsten 5 molecule, indeed you can measure a decoherence time at 0 applied magnetic field. But then to make sure this is indeed what we hope and think it is, we apply a relatively small magnetic field, and then you see all of these coherent oscillations grow in with that perpendicular magnetic field. So this shows that the electron spin coherences are being generated and detected all optically in this system. And interestingly, going from iridium-4 now to a tungsten 5 system, we're moving through the periodic table. We're changing the chemical properties of the molecule. And in doing so, we prolong the coherences. In iridium-4, that complex had a decoherence time of about 10 picoseconds. This has a decoherence time of about little longer than 2 nanoseconds. So many orders of magnitude improvement of time. So we still want to be able to measure, you know, femtosecond resolved coherences, because those femtosecond resolved coherences are sensitive to specific chemical microenvironmental phenomena. But as we now prolong coherences in molecules, we can now detect other types of things. So for example, here's data at 0 magnetic field, here's data taken at 5 millitesla. So very, very small magnetic field. It's not quite to the value of Earth's magnetic field, but it's a very small magnetic field. We would never be able to detect this with the iridium-4 complex, for example. So this is just a DC, you know, no variation in the magnetic field. I think if we go to AC field sensing, lock-in detection, we could probably, I don't have a quantitative calculation for this, but we could probably get to Earth's magnetic field, and this is something we're working on currently. So being able to detect minute changes in magnetic fields and hopefully someday also electric fields is something we're really interested in. And we've already gotten to this point with the tungsten 5 complex that I've shown you. And then I'll just sort of finish up by showing you a couple of other really exciting examples, current unpublished results in our group. We can go to a little different structure here, this palladium-1 complex. So the unpaired electron in the iridium complex sat on the iridium-4 center. In the tungsten 5 complex, it sat on the tungsten 5 center. This is a palladium-1, and the unpaired electron sits on that palladium-1 center. This is actually a catalyst used for cross-coupling reactions, so making molecular pharmaceuticals, making drug candidates, very heavily used in industry. And so for a variety of reasons, we're interested in this from the coherence detection side of things, but also thinking about using coherence as a new way to study chemical reactions. So this kind of accomplishes both of those things at the same time. But the nice thing here is, really it was confusing at first, but what Sojung and Erica in my lab measured was now you can see these oscillations at 0 magnetic field, and then you see these sort of funky patterns grow in as a function of magnetic field. And even up at 0.2 Tesla, we see the case where the coherence decays, goes away, and then it comes back, and then it goes away, and then it comes back. Really interesting observation. And so what this boils down to is essentially the interaction of the electron spin, right? The electron spin is like a tiny little magnet, right? Little magnetic field associated with it. And the nuclear spins of the phosphorus ligands, these phosphine ligands, bound to the palladium-1 center. So phosphorus has a nuclear spin of 1/2, and therefore the nuclear spin also has a tiny little magnetic field. And so they can sort of talk to one another. And so the way we're interpreting this right now is these sort of beating frequencies are kind of like an echo, right? Where the electron spin coherence is generated on the palladium center, and then it goes off and it interacts with the other parts of the molecule, in this case the nuclear spins of the ligand, and then it comes back, and then it goes back and forth and oscillates between different parts of the molecule, which is really, really fascinating to think about, and I think will open up a lot of really new sensing modalities, and it's also a fundamentally new way to study electron-nuclear spin interactions in molecules. So I think a lot will come of this fundamental observation as well. And then I'll finish with an observation and discovery that Chris is also here today, a graduate student in my group made along with Erica, a postdoc in my lab, studying plasticyanin. Coincidentally, this is the first protein I ever studied in my PhD, and everything is cyclical, and so here we are studying it again. But plasticyanin has a copper 2 center. The copper is sitting right there, and the unpaired electron sits on that copper center. It shuttles between copper 2 and 1 redox states and acts as an electron transfer partner between cytochrome B6F and photosystem 1 in photosynthesis. So now we've gone from molecules to biology. So that's a big step. And we've gone to a very important electron transfer photosynthetic metalloprotein. And so Chris can actually go and express this protein and purify it and get lots of this protein. And you can now think about the implications of actually being able to genetically encode these biological quantum sensing modalities. We're not there yet, but I mean, in principle, it's already, well, I guess it's kind of there because you can, you use the molecular biology techniques to express and purify this protein in E. coli. So we can measure the electron spin coherences in the absence of a magnetic field and with an applied magnetic field. And so we've been able to kind of crack into these biological systems in this manner. So that's also extremely exciting to think about the potential applications moving forward. And so to sort of summarize, we've gone from the initial discovery with these high symmetry iridium-4 complexes, which have a certain property called spin-orbit coupling in the ground state that allows them to be active for this technique. And we've shown how to lower the symmetry to tungsten-5 complexes to expand the synthetic scope of molecules we can study with this technique. And we do this by moving that property of spin-orbit coupling into the excited state. And then we've gone from lower symmetry synthetic molecules to now biological systems. In this case, a copper metalloprotein, which also shows this spin-orbit coupling in the excited state. So we've been able to decrease the molecular symmetry, increase metal abundance, and ideally increase the application scope as we go across this series. And again, this is all just done in the last couple of years. And so I anticipate a lot of really rapid and exciting developments. And in that regard, I'll sort of wrap up by saying we've developed this new way to measure molecular coherence across chemistry. I'm talking about our material science applications, but I think there's a lot to do there and in biology. And just as magnetic resonance imaging transformed nuclear spins into images of the body, our group aims to transform molecular quantum coherence into these femtosecond resolved images of diverse chemical environments. And we're hoping to apply these to materials and their interfaces to study interfacial dynamics, hopefully collaborate with people and think about how we can apply these techniques to issues in neurobiology, membrane electrostatics, imaging subcellular magnetic fields, and studying photosynthesis and protein dynamics. And so with that, I want to thank my group, outstanding group of people. It's just been so rewarding to work with them, see how they work together. It's a very interdisciplinary group. Everybody brings some capability to the table, and we go from molecular synthesis to biology to pretty hardcore instrumentation and electronic structure analysis in the group. And so I tried to highlight those folks who had contributed to the data I presented today. And of course, thank you all for your attention.
Thank you so much, Professor Hadt. The questions are coming fast and furious, so let's see how many of them we can get to.
Sounds
Dean
good.
Dogger, PhD. To what extent does photosynthesis leverage quantum effects such as tunneling? Is that something your research can help answer?
Yeah, I think that's a wonderful question, and I think it's actually somewhat controversial. So there have been what are called vibronic coherences measured in photosynthetic systems, essentially the coupling between electronic structure and actual atomic motions in photosynthetic systems, in chlorophyll, for example. And that vibronic coupling is thought to help facilitate electron movement and energy movement through photosynthetic systems. So there's vibronic coherences. There's also aspects of electron spin coherences that have been thought to be interesting in biological systems writ large, not just photosynthesis. And that's something called chiral-induced spin selectivity, or the cis effect. And that has to do with how electrons move through chiral media, right? So proteins are made up of amino acids, which I think we'll hear more about the role of the handedness of amino acids in a talk later today. And so it's thought that the chirality of the medium actually affects how electron spins move through that chiral media, again, the chiral-induced spin selectivity. And the underlying nature, or the mechanism, if you will, of the chiral-induced spin selectivity is thought to relate to these similar types of electron spin coherences. And then I'll also just mention that time-resolved electron paramagnetic resonance has been used, even though it has a slower detection limitation, to actually detect electron spin coherences for charge-separated states in photosynthetic systems. So sort of the long-winded answer is these types of questions are active areas of research, and I really do hope that we can one day use this technique to actually study a biological system to show whether or not we can generate and detect electron spin coherences, and to see if those electron spin coherences actually interact with the vibronic coherences, in a way that might manifest also in this chiral-induced spin selectivity effect. So, wonderful question. It's sort of at the heart of a series of questions, but I do think that this technique is ideally suited for trying to answer that question.
Mark Adler, PhD 90. If millisecond scale quantum coherence is possible in molecules at room temperature, could biology already be functionally applying it somehow?
I think that yes, I do think that speaks to the previous question. Absolutely, I think that if an electron transfer protein in photosynthesis, for example, were leveraging spin coherences, it's certainly possible. And if you go to many biological systems, the medium that the electron is transferring through is organic, right? So we're going from, we talked about iridium, which has, again, I'm going to use this term spin-orbit coupling, essentially how the electron angular momentum of the spin couples to its orbital angular momentum. It's not super important, but it's very large in transition metal complexes. And that spin-orbit coupling can also intrinsically lead to decoherence. And so if you go to something that is now going to iridium-4 to tungsten-5, that decreases the decoherence by decreasing the spin-orbit coupling. And then if you propagate that to an organic molecule, so if we can get this to work in an organic molecule, you might actually see millisecond time constants for decoherence. And certainly, I think it's possible, but the experimental data proving that I don't think exists currently.
Increased viscosity from glycerin implies more collisions in Brownian motion. This should reduce coherence, yet results say the opposite. Why?
I mean, I've thought about this question actually. I think it's a good one, and I think that it really boils down to the mechanism of decoherence. And basically, your question asks, how much does molecular rotation give rise to decoherence versus another molecule colliding with that molecule? And so I think the data says that molecular rotation contributes more than molecular collisions do to decoherence rates. Certainly an interesting thing to potentially study. One would have to differentiate between the collision rates and the rotational rates, but we're all about quantifying mechanisms, so I think that would be an interesting thing to look at, actually. Yeah.
Last question. It should be noted that you're going to give some tours in your lab today, so then you can ask, if you can find Ryan, you can ask all of your Project Hail Mary questions, of which there are many. Okay, but
I've read that book, so
yes.
I haven't seen the movie.
You haven't seen the movie, read the book, and those, just in terms of your tour, we're excited to tour your lab today. My question is, what's possible for your work at Caltech that isn't possible elsewhere? Last question.
This.
And on that note, succinct yet perfect, thank you, Professor Ryan Hadt, for your excellent talk. Thank you. And we're now heading into our first elective block. There are 3 student-led options before lunch, all running in parallel from 11:45 to 12:20. The 3-minute thesis challenge. Boom, Caltech grad students get 3 minutes and 1 slide to explain their research. No jargon. The format is unforgiving, content informative, the results often genuinely funny. And to test you, of course, in the program, the location is wrong, just to have fun with you. We know you're so smart. It's correct on the screen. It's Gates Annex B122. So if you want to do the 3-minute thesis challenge, Gates Annex 122 is right. Then also the Eberhardt Distinguished Graduate Student Lecture, a longer form talk from one of Caltech's strongest grad student communicators, designed to make sense across disciplines. And that will be in Noise 153. And finally, you can stay right here for the Perpall Surf Speaking Competition. This year's winning undergraduate researchers selected from nearly 200 surf presentations. Pick one, no wrong choice. Which you try to attend all 3 at once, wait for a joke, in which case, congratulations. You are reliving freshman course registration. You are reliving freshman course, okay, all right.
Well, good morning, everyone. My name is Vincent Tan. I'm a program manager in the Caltech Student Faculty Programs Office, and for nearly 50 years, our office has been known for overseeing the undergraduate research programs at Caltech. Many of you know us through the Summer Undergraduate Research Fellowships Program, otherwise known as SURF. SURF this summer is entering its 48th summer, but this past summer, in summer 2025, over 770 students participated in our research programs working here at Caltech, at JPL, and all around the world. Over 400 of those students participated in the SURF program. Each summer, hundreds of Caltech undergraduates engage in cutting-edge research alongside the Institute's faculty, graduate students, postdocs, and staff scientists. Today, you'll hear from two of those students, both finalists from the 2025 Doris S. Perpall Surf Speaking Competition. The Perpall competition was established in 1994 by Caltech alumnus Bob Perpall in memory of his late wife, Doris, who was deeply invested in helping students communicate their ideas in a clear, enthusiastic, and effective manner. Establishing the competition over 30 years ago was only one of many contributions that Mr. Bob Perpall made to this community. Over the course of his life, he provided leadership to numerous organizations, including the Alumni Association, the Caltech Associates, the Caltech Y, and of course, the SURF program. Our first speaker today is Dia Kumar, a fourth-year astrophysics student and planetary science student who conducted her SURF research with Professor Fei Dai from the University of Hawaii. Dia's associate mentor, her Caltech mentor, was Professor Lynn Hillenbrand, a professor of astronomy here at Caltech. Dia took home first place at this year's Perpall Surf Speaking Competition, and you're really in for a treat today. Please join me in welcoming Dia to the stage.
Thank you, Vincent, for the wonderful introduction. I can't tell you how exciting it is to be speaking on the big stage about one of my favorite topics, which is planet formation, and to share it with all of you guys. This is really only an opportunity that's available at Caltech, as I'm sure many of you already know. It's a very special school, and I'm so grateful to do this before I graduate. So my name's Dia. I'm a senior at Caltech. I study astrophysics and planetary science, and this summer I worked in Hawaii with Professor Fei Dai on a project we call the Dynamical Disruption of Resonant Chains. Maybe the clicker isn't working. Should I just click it here? So, So I like to start these talks by talking a bit more broadly about why we study planet formation. Like, why is this field so exciting and so interesting, even though it's so far away from us? And the first is to understand what exoplanets are. So exoplanets are just planets that orbit stars that are not our sun. So they're planets that are outside of our earthly neighborhood and are outside of our solar system. And it's really exciting because the first exoplanet was only discovered 30 years ago. Now, this is really, really recent, especially for a field that's so booming, and one that encompasses all of humanity now. In fact, now there have been over 6,000 exoplanets discovered, and with every one, our understanding of planet formation dramatically reshapes. In fact, the first exoplanet we discovered around a sun-like star was what was called a hot Jupiter. Now, these are Jupiter-sized planets that are closer to their stars than Mercury is to our sun, which is insane. Like, for us to discover this, that it falls so far outside of the frameworks that we've come up with for our own solar system. And since then, we've discovered so many strange things in these exoplanets we've discovered. We've discovered super-Earths, which are bigger than Earth but smaller than Neptune, sub-Neptunes, which are like these weird puffed-up versions of almost like a middle between Earth and Neptune, and we've discovered resonant chains, which is what this talk is about. And of course, this begs the big question of like life outside of Earth. We've not yet found a solar system analog, yet we're looking for life that looks similar to us. And so it makes us wonder, potentially, maybe we're looking for life in the wrong ways. Maybe we need to go back to basics and understand how planets form and why they look so different from us, so we can better understand how we can find life like ours. Okay, so to understand this topic, we first need to go over what resonant chains are. So resonant chains are planetary, basically chains of planets, where each pair orbits at an integer period ratio with its neighbor. And so an example we see in our own solar system are with the 3 moons of Jupiter, Ganymede, Europa, and Io. So for every 2 orbits of Io, there's almost exactly 1 orbit of Europa. For every 2 orbits of Europa, there's almost exactly 1 orbit of Ganymede. So that means that these moons line up every 4 orbits of Io. Now, this is a really mathematically beautiful outcome of physics and astronomy. And Kepler and Pythagoras actually saw this and thought, the universe must have been created under intelligent design, and that the most intelligent design is mathematical, and it has to be this resonance. Kepler actually called this the harmony of the worlds because he found it so beautiful and mathematical. So what do we see observationally? We see that most systems are born in resonance. So 90% of young systems are resonant. But we see that as they age, the fraction of resonance drops quite steeply. So 40% of adolescent systems, like I call them teenage systems, are in resonance, and then only 20% of mature systems are in resonance. Now, I call mature like 1 billion years old, and for context, our solar system is 4 billion years old, so it's in that mature category. But this is a puzzle, right? Why do these systems break apart as they age? How do they break apart? What does this tell us about planetary stability? And what can we learn from this about our own solar system and where it kind of fits and slots into the wider picture of planets we've now discovered? So there's a very famous system called TRAPPIST-1, where all 7 of its planets are in this mean motion resonance with one another. And by the way, this system is older than our own, so it fits into that 20% of still resonant category. However, our own solar system, the only real mean motion resonance we see is with the moons of Jupiter. So it's curious why planetary resonance was able to survive in TRAPPIST-1 and not in our own solar system. And that's something that we can understand and uncover with the research that we're doing. So to understand how resonances break, we first have to understand how planets form and how resonances form. Now, I love the topic of planet formation, and I could give a whole talk just about that. But for the sake of getting to my own project, I found an infographic that kind of sums it up very nicely, and we can go through it panel by panel. So planets form in a gas disk around the star. Now this disk has gas and it has dust, and closer to the star it's a lot warmer, so you get rockier dust grains that are more bare. So these, when they start to stick together, they can't coalesce into big enough planets since the dust grains just aren't sticky enough. So we get smaller planets further into the star, and they're more rocky and they're more arid. Further out, it's a lot colder. So you get ices that condense, you get water that condenses, and you get methane and CO2. And those dust grains are coated in layers of ice and that are more sticky, so you can get bigger planets like what we see in our own solar system, and they're more volatile rich. Now, as these planets are forming, they're also interacting gravitationally with the disk. So there's angular momentum exchange between the planets and the gas around the disk, and they start to migrate. They start to move through the disk while the disk is still present. Now, as they move, some move faster than others because of their mass and the way that they're moving, their speed that they're moving at. And so they interact with one another gravitationally because they come into contact with one another. Now, when they pass through this resonance, because the kicks are so coherent, since it happens every set number of values, they lock into this resonance. Only about 90% of planetary systems actually lock into this resonance, but that's still a big fraction of them that kind of just fall into this resonant ratio. But the idea is that after this gas disk dissipates, most of the systems go unstable and the resonances are broken. But why do they break? That's what this talk focuses on. We think that the gas that kept the system stable is now gone. And so tiny gravitational nudges between these planets that were really small and actually helped them lock into resonance as the gas disk was there are now amplifying because the gas is no longer there as like a damping force. And so the resonances can break, leading to chaos. Now, a good way I like to think about tiny things having a big effect is with a double pendulum. Now, a double pendulum is just like a normal pendulum that oscillates around an equilibrium point, but it has another pendulum attached to the bottom of it. And it's a very good marker for chaos because the behavior is really unpredictable. So the idea is if you start multiple double pendula right next to each other, almost at the same starting initial conditions, but slightly different, you'll get wildly different behavior as they evolve. So I have a video of that to show you guys. As you can see, they look like they're evolving the same way, but over time, the tiny changes in the beginning lead to completely dramatic divergence that we can't predict. And so that's an example of small things having a big effect over time. So how do we mathematically conceptualize this resonance? Like, what do we look for in the data that tell us when resonances break? And that's to do with the resonant angle. Now, the resonant angle is a combination of orbital positions and orientations, and it basically just says, well, how do these two planets line up over time? So resonance, as I mentioned, is when the period ratio of two planets is near an integer value. However, there's two types of motion for planets near the resonant. There's libration and there's circulation. Circulation is when the period ratio is near p to q, where p and q are some integer value, like say p is 3 orbits and q is 2 orbits. That's when they line up. So the period ratio is near p to q, but these planets are not locked in resonance. The resonant angle is able to keep increasing, exploring the entire 0 to 360 degree parameter space. This is kind of like if you were to swing a ball over your head, it's able to explore the entire range of values. Libration is when the period ratio is near p to q again, but these planets are locked in resonance. This is like a classic pendulum. It's oscillating around an equilibrium point, and it can only access some finite range of values. But why do we care? Like, why do we make the effort to define circulation versus libration? It's because it has real implications for stability. So circulation is destructive. If you can imagine, the resonant angle is able to literally take on any value in its parameter space. This means that the orbits can drift freely. At the point of their conjunction, the orbit can take on any phase relative to the other planet. So they can even come very close and potentially even collide, which is destructive, of course. A smaller scale thing that can build over time is these tiny orbits' gravitational pushes to one another will not align over time because they happen at different points in their orbit. So those tiny differences in the point at which they kick one another gravitationally will amplify over time, causing chaos. Now, libration is protective. The motion in this case is phase locked. So that means that the conjunction happens at similar points in their orbit every single time. So their gravitational kicks to one another will cancel out and they'll be stable. Additionally, the planets will never get too close to one another because of this timing protection. Now, a really good example of this is in our own solar system, if you still consider Pluto a planet. Neptune and Pluto are in a librating resonance with one another. But that's important because their orbits actually cross. Now, we do not want that. We never want orbits in our solar system to cross, especially ones with a planet as big as Neptune. But the reason we don't talk about this enough is because it's stable, since it's in the librating resonance I mentioned. Every time Pluto is near us, Neptune is super far away, and every time Neptune is near us, Pluto is really far away. So that means we don't really have to worry about this happening because of this resonant protection. Now, what did I work on this summer? A previous work of my mentors found that resonant chains form via this disk migration that I was telling you guys about earlier. And so they use simulations to show that as these planets migrate, they'll lock into resonance. Now, this has been shown now with simulation, with theory, and with observation, like the 90% of systems form in resonance slide that I showed you earlier. So I use the end of their simulations as my initial conditions to now discover how they might break. I use Rebound, which is an n-body simulation library, and it's very widely used. It's even been used to show that our solar system is classified as a chaotic system, but not on the timescales that we're around for it, so it shouldn't be much of an issue. And it's also been used to kind of support the existence of the NEAS model. Now, the NEAS model is a model of our early solar system's evolution. It basically said our early system's evolution was very chaotic because Jupiter and Saturn were passing through a resonance in their early solar system. Because they broke out of that resonance, they didn't quite get captured into it, they caused a lot of chaos. They scattered a bunch of planetesimals, which are the building blocks of planets, from the outer solar system where they exist to the inner solar system where our Earth and the Moon is. Now, we see evidence for that observationally because of all the cratering on the Moon and the cratering that was on Earth, which has been kind of wiped over by tectonic activity. Now, I use Rebound. I create a simulation framework that tracks resonant angles over time and tracks the orbital elements so we can decode what's happening. Now, this is an example of a librating resonance. As you can see, the resonant angle increases and oscillates with such a small amplitude that it looks like it's almost constant for all of these pairs of planets. So even visually, this looks very stable. This is a circulating resonance. Just visually, it looks so much more chaotic, right? It can explore the entire parameter space, 0 to 360 degrees, and that already looks destructive, despite me telling you that it is destructive. So what are we working on? We're working on long-term integrations of these planetary systems out to maturity, which, as I mentioned, is 1 billion years. The reason for this is we need to explore whether resonance is breaking early is different than resonance is breaking later. And also, we can really explore when resonances break relative to what we see observationally, as well as how they break. And of course, this contributes to planet formation theory because we've never actually fully understood how resonances break. There's been a lot of efforts that come up with different methods as to how they break, but long-term integrations will really nail it down, whether it's a late stage process or an early stage process. So I have some intermediate results to share with you. And I use what's called the Lyapunov timescale. So the Lyapunov timescale basically says, how quickly does a dynamical system lose predictability? So a long timescale is a stable system. That's because it loses predictability a lot slower. We know what's going to happen in the near future, so we're not too worried about it behaving in a chaotic manner. A short Lyapunov timescale is a chaotic system. It goes unpredictable very, very fast, so we don't know what's going to happen in the near-term future. So to understand the results, there's two types of chains I want to present to you. The first is a full chain. That's when every pair of planets is near this integer ratio, and each pair of planets is librating. A partial chain is when only some of the planets are in an integer period ratio and only some of the angles are librating. So this means that only part of this chain is in full resonance. So from the Lyapunov timescale, we see that 98% of them, 98% of the full chains, when every part of it is librating and in resonance, is regular. So that means we can predict what's happening for about 98% of these systems. And 2% of them are chaotic. We can't really predict what's going to happen, so they might lead to collision or destruction. This is a partial chain. We can see that about 76.5% of them are regular, so we can, for the most part, predict what's happening, but already 23.2% of them are classified as chaotic. And that means that maybe partial chains themselves are the links to instability in these planetary systems that we're seeing. Perhaps these small imperfections in a chain, with them not being in resonance, like cascade over time, like the double pendula I showed you earlier, and cause them to break out of resonance like we're seeing observationally. So what are some takeaways? we know that these systems begin stable. We see it observationally, we see it theoretically, and we know that they begin resonant as well. We also know that the disk has to dissipate. It can only last a few million years before it gets engulfed by the planets and just dissipates into the interstellar medium. So we know that the damping in the disk will lessen over time. We also saw that partial chains are more chaotic. And if you think about it, if the disk can only last a couple million years and planets take time to form into full resonant chains, it might be true that more planets are caught into partial chains than full chains. And that could explain why we see this resonance breaking. Additionally, we see that small perturbations are growing into chaos. These small instabilities, like a very large libration amplitude or a circulating angle when the planet forms, can lead to them going chaotic or even just colliding. So stay tuned, the long-term simulation is running. As I mentioned, we're running them out to 1 billion years, which, as you can probably imagine, is very computationally expensive and time-consuming. And we really want to investigate how these resonances break. Do they break all at once? Like, does part of the chain break and then the rest of it just immediately breaks? Or is it that they break episodically? Maybe part of the chain breaks and the rest of the chain remains unaffected, so the breaking is more localized. Or maybe it's that part of the chain breaks and that effect cascades down to the rest of the chain over time, causing everything to go unstable, but on different time scales. Now, this is important because it could lead to really important results like what we saw in our early solar system's evolution. If part of the chain breaks, you can imagine that it could cause a lot of debris to come flying inwards and cause mass cratering and impacts, like maybe the one that killed the dinosaurs. But we could also have positive impacts. If part of the outer chain breaks, the part that's in the volatile-rich region, like I mentioned earlier, with ice and water, it could bring volatiles to the inner solar system where it's more dry and arid, potentially creating sites for life to form, which would be a very exciting result. So ultimately, this helps us understand observational results and help support what we see with why we see it. So I would like to thank everyone who helped me with this project, my professor in Hawaii, Fei Dai, a grad student who helped me, Mu-Tian Wang, of course the Caltech SFP office and the Alumni Association, and the University of Hawaii's Institute for Astronomy, I like to say, for letting me surf during my surf. And of course, my family and my friends for listening to this talk like a million times. And my dad, who's here right now watching. Thank you.
Well, great. Well, great. We have some good audience questions that I will ask you.
Okay.
I'll throw you a pretty good one right here. What a fascinating presentation. What's next for you after Caltech?
Oh, that's a great question. So I'm graduating this year, as I mentioned. So I'm doing a Fulbright in Germany. I'm working at the Max Planck Institute for Solar System Research. So I'll continue my planet formation journey. And then I'm doing my PhD at the Lunar and Planetary Lab in Arizona, which is so exciting. Back to the heat.
You ran a couple of the simulations on the deck.
Yes.
If you had unlimited computing power, what would be the next simulation that you run?
Oh man, I would first try and run all of them at once. Like right now I have to separate them because of how long it takes. So I would run them all. I'm also thinking of adding like a giant planet in the outer part of the chain, like kind of like Jupiter is to our solar system, because the gravitational effects from a giant planet could potentially cause a lot of cascading events in the inner system that hasn't been fully explored yet. But of course, that's another particle in the simulation, so I need to think about how to do that.
How does rebound address the breaking the chains hypothesis?
Yes, that's a great question. Rebound is more of like a simulation framework, so it integrates under gravitational interactions of planets. And so using rebound, we can run simulations that address how these resonant planets break. But I would be happy to talk about breaking the chain with whoever wants to after this talk.
Yeah. Does the timing of gas disk dissipation predict which systems survive long term?
That's a good question as well. There's been a lot of work that shows that the instability in these planetary systems happens during the gas disk phase. So there's a lot of papers that implement very detailed gas disk dissipation models that show that most of these systems go unstable. However, I think because of what we're seeing, that the systems break at different points in their lifetime, that certainly can't be the only thing at play. So what I'm trying to do is focus on the long-term integration for later stage breaking, though I've tried different gas disk timescales, and I'm seeing similar results across my simulations. So I think it's mostly an effect of early system breaking rather than later system breaking.
Now, does your model predict mature partial chains that we can observe?
Mature, oh, like older partial chains?
Right.
Yes, it does. So a lot of systems are in partial resonance. Like I said, if you consider Pluto as a part of our solar system too is a partial chain, right? Part of it is in a librating resonance. So my model, as I've run it so far, it's come up to like 100 million years, I think, for some of the systems. And the partial chains do survive. It's just partial chains in the beginning seem to contribute to a lot more breaking than full chains in the beginning. So I think partial chains can be the outcome, though they cause a lot of destruction early on in their path.
Other than maybe talking to you, where can I learn more about resonant chains? This is super interesting.
Yes, I actually have a podcast because I love space so much. It's called Spaced Out. I would love to share it after this talk, but I have a podcast episode about this, and I've written an article about it too if you want to read it.
We're on the same wavelength. I wanted you to plug your podcast. See, I didn't even have to tell her anything.
Yes.
Outside of maybe being at Hawaii, or maybe that is your favorite part of the research, what were some of the favorite parts of your summer last year?
Yeah, of course I loved being in Hawaii, though I tell my friends and my family that it felt like I was on a vacation every day. So it's quite hard for me to get focused and not be on the beach. So that was one of my favorite parts. But I will say, I love doing this large-scale simulation so that I could really put all of planet formation into the picture and fit the pieces of the puzzle in, rather than looking at individual systems and trying to slot them into a bigger puzzle. I was looking at the puzzle as a whole, which was really fun and exciting.
Okay, we have a couple more questions. Are some MMRs more fragile than others? Does a 2-to-1 ratio break differently than a 3-to-2?
Yes. For context, to people that forgot, MMR is mean motion resonance. It's just that resonant ratio that I was talking about. And that's a really good question. I think rather than certain MMRs being more fragile, which I still have to investigate through the simulation, it's more the resonance order that matters. So resonant order is basically how different are the number of orbits from one another. So say the inner planet does 5 orbits and the outer one does 7. The difference between those is 2, so that's a second order resonance. The difference between them being 1 is a first order resonance, and so on. So in my simulations, we have first, second, and third order resonances. And we see from theory and physics that higher order resonances are more fragile. So potentially the order of the resonance matters more than the numbers involved in the resonance, because if there's a higher order resonance in the chain, it can be more susceptible to breaking, which is cool.
Great. And before I ask our last question, I just want to put a spotlight on some of the alums that I see today. I see Dr. Susan Murakami, a huge supporter of our SURF programs. Dr. Murakami actually serves on our SURF board, so thank you. One of the big supporters as to why the Perpall's speakers are invited to Seminar Day, so thank you, Dr. Murakami, for that. Dia, as you wrap up your time here at Caltech, what has undergraduate research meant to you, and how will it affect that really exciting future that you have planned?
Yeah, I loved coming here for the undergraduate research. It's a great question. I've done a SURF every single year of being here, and it's taken me all over the world, literally. So I did my first SURF at JPL. My second SURF, I was living in Sydney, Australia, and then I was living in Hawaii. So this has meant so much to me past just doing research. It's like I'm like exploring and growing as a person. So it's meant a lot, and I think it's really propelled me towards wanting to do research in the future, which is why I'm doing research in Germany now, which is something I probably would have never done if I hadn't gone all over the world for my surfs. And of course, doing a PhD, which is a big commitment, as I'm sure many of you know. But doing a PhD and doing the research and being excited to share it has all stemmed really from my experience with surf. So thank you all.
Well, great. I hope you'll all join me in thanking Dia for a really great talk. And I believe the next thing on our program is lunch. We hope you'll have a good lunch, and we'll have another Perpall speaker here in Beckman in the afternoon. Thanks for joining us, everybody, and thank you, Dia. Well, good afternoon. My name's Vincent Ton, and I'm a program manager in the Caltech Student Faculty Programs Office. For nearly 50 years, the Student Faculty Programs Office has overseen the undergraduate research programs at Caltech, and many of you likely know us through the Summer Undergraduate Research Fellowships Program, otherwise known as SURF. In summer 2025, over 770 students participated in our research programs, with over 400 of those students participating in SURF. Each summer, hundreds of Caltech undergraduates engage in cutting-edge research, working alongside the Institute's faculty, graduate students, postdocs, and staff scientists. And today, you'll hear from a couple of those students. Earlier today, we had a talk with one of them. Here's our second student this afternoon. Both of those students were finalists from the 2025 Doris S. Perpall Surf Speaking Competition, which awards the Institute's top prize in undergraduate science communication. The Perpall competition was established in 1994 by Caltech alumnus Bob Perpall in memory of his late wife Doris, who was deeply invested in helping students communicate their ideas in a clear, enthusiastic, and effective manner. Establishing this competition 32 years ago was only one of many contributions that Bob Perpall made to this community. Over the course of Mr. Perpall's life, he provided leadership to numerous organizations, including the Alumni Association, the Caltech Associates, the Caltech Y, and of course the SURF program. Our speaker this afternoon is Chiara Ozturk, a second-year chemistry student who conducted her SURF research with Professor Jeffrey Reimer from the University of California, Berkeley. Chiara's associate mentor, the faculty mentor who supported her here at Caltech, is Professor Paul Wenberg, who is the Institute's Avery Professor of Atmospheric Chemistry and Environmental Science. I hope you'll join me in welcoming Chiara to the stage. You're in for quite a treat.
Hello everyone, my name is Chiara Ozturk, and today I'm very excited to present to you all the summer research that I did at UC Berkeley's Reimer Lab last summer. Last summer, I investigated the molecular geography of climate stress, where I essentially used NMR and machine learning to find a bridge between conifer health and climate health. So just a really quick overview of this presentation, I'll first be delving into the background and the research problems that we were trying to solve this summer, delve into the specific 2 research questions we focused on, talk a little bit about the machine learning models we used to implement to solve this problem, and finally conclude with the results and next steps for this project. So I know it's been a while since you guys have been on Caltech campus, but I hope during your undergraduate years, you had the opportunity to really enjoy the Californian outdoors. As a California native, I've had the opportunity to go to a variety of national parks in this area. And in particular, one common thing that I recognized across these parks was the gorgeous conifers in these areas. Conifers serve as a crucial crutch for a lot of ecosystems, as they serve as a natural habitat for multiple species, while also being an important carbon sequesterer. Unfortunately, in the past couple of years, climate change-induced events have significantly impacted these conifers, ranging from severe drought to intense wildfires. But the issue is, there doesn't really exist a quantifiable method of really understanding how these conifers are responding to these environmental stresses and situations. How healthy are these conifers in response to all of these things? So potentially, we can maybe analyze a certain substance that these conifers emit in a way that can provide us the answers to these conifer health questions that we have. And in particular, this substance that we want to analyze would satisfy 3 criteria. First of all, it should be scalable so that we can collect it across a variety of conifers in our California ecosystem, and also in a non-invasive manner. We don't want to actually hurt these trees while we're performing our research. Secondly, they should be able to be stored long-term so that we can perform multiple experiments on them as well. And finally, their chemical composition should be relatively simple to analyze. And lucky for us, tree resin satisfies all 3 of these criteria. For lack of a better analogy, I like to think of tree resin almost as tree pus. When these trees are exposed to significant environmental stresses, they secrete this compound as an immunal response. So potentially, the overall chemical composition of this tree resin provides us the answers to what we're looking for about conifer health. And lucky for us, a couple of researchers in 2006 had the same idea as well. So what they did was, they collected a variety of tree resin samples across various conifers in Norwegian forests and performed an experiment called LCGMS, where they essentially ionize these tree resin samples to get an overlying understanding of the chemical composition of this tree resin. Now what was really interesting, Now what was really interesting about these experiments is that when they plotted these spectra onto a principal component analysis plot, which is designed to maximize the variance across these spectra, they saw coupling between the different tree resin spectra and the corresponding drought level exposure that these trees felt. So overall, they found a connection between this tree resin chemical composition and the drought exposure that these trees were exposed to. So we wanted to see if this was the same case for our trees in our California ecosystems. So we collected 200 tree resin samples from a variety of trees in California, Idaho, Wyoming, Oregon, and Washington, and dissolved them all in deuterated chloroform. So now that we have all of these tree resin samples, what can we really do with them to really understand conifers and how they're responding to the environmental stresses that they feel while they're in California? So potentially, we can use a non-invasive chemical technique in order to analyze these. What the researchers did in 2006 was very novel. It was very impressive. But they used this very invasive technique of mass spectrometry, where they essentially burned all of these samples to understand the underlying chemical composition. For me personally, I view my tree resin almost as liquid gold. It really is hard to go out into the open and to collect these samples. So potentially, using a more non-invasive technique could still provide us the answers that we're looking for. And lucky for us, we can use nuclear magnetic resonance spectroscopy. This is a type of chemical technique where essentially we're using the power of magnetic fields to really understand what is the actual composition of our tree resin. So in this experiment, we essentially shine a magnetic field on our tree resin sample. All of the protons in this sample are aligned in the Z direction. And when we apply a radially labeled frequency pulse, we push all these spins to lie perpendicularly on the XY plane. As these spins are relaxing back to their original state, they basically rotate at something called their Larmor frequency. This frequency corresponds to the overall chemical environment that these protons are exposed to. And the signal they emit can be detected by a detector. And the signal is called a free induction decay. Through applying an analysis technique called fast Fourier transform, we can essentially convert all of these sinusoidal signals into a spectra, where all the peaks provide us really critical information about the overall tree resin chemical composition. So we performed NMR on all of our resin samples. We collected 1D proton NMR spectroscopy, where all of the individual peaks correspond to different functional groups that are actually present in our samples. And we also performed 2D correlational spectroscopy, which gives us a lot more spatial information about where these individual protons are in the actual resin sample themselves. Now, with all of this data in hand, how can we really optimize this data so that we can really find this underlying conifer health problem that we're trying to solve? This brings us to our 2 research questions this summer. First, how can we use this NMR data and machine learning methods to develop a classification framework where we can classify trees into their respective burn and drought statuses? And secondly, what if we develop a more novel method, something that's never done before? What if we develop a more chemically non-invasive method of actually identifying what chemicals are present in these samples without destroying them using machine learning? Moving on to our first research question. We have all this 1D spectra with a lot of information about the functional groups. Now, how can we use that to classify these trees into their respective burn and drought statuses? Now, what I mean by burn and drought statuses is we have a binary level of classification. Are these trees burned or unburned? Or are these trees exposed to a level of drought, or are they in no drought? And to solve this classification problem, we decided to approach this using neural nets. So just a very quick overview of a neural network. We can essentially think of this for architecture as having 3 main components: an input layer, hidden layers, and an output layer. All of these layers are composed of nodes, and these nodes are connected to each other with a series of weights. One way we can think about each consecutive layer is that it's a linear combination of all of the nodes in the past layer. And the whole goal of a neural net is to basically optimize all of these weights so that we can get the highest level of classification accuracy. Now, how does my binary neural network actually classify my tree resin spectra? Let's take a quick example. Tree 5 is a burned tree, while tree 2 is an unburned tree. And in regards to classification, we take a look at the output layer, which consists of 2 nodes. The first node has the value that corresponds to the probability that the tree is burned. So ideally for tree 5, this value would be a lot higher than the value in the second output node, which corresponds to the probability that the tree is unburned. And ideally for tree 2, we would have a higher value in that second node compared to the first node. So we fed all of our data, all of our tree resin spectral data into our neural networks. And then we did 3 different types of classification schemes to test if the neural network can successfully classify these trees into their burn status, their drought status, and drought zones. And what I mean by drought zones is essentially Californian and Western US ecosystems can be classified into different drought zones based on the level of drought that these trees are exposed to, ranging from D0 to D5. D0 corresponds to just an abnormally dry environment, while D5 corresponds to intense levels of drought. Now, what was really interesting about the results from our neural network was that, first of all, we had 98 to 100% classification accuracy for all 3 classification frameworks, indicating that these neural networks were actually able to classify our trees into their respective burn and drought statuses based on their spectral data. But something even more interesting was that when we plotted principal component analysis, like those 2006 researchers did, we actually identified clustering between the different trees and their corresponding statuses. And what this is telling us is this tree resin spectra actually has key components that change when these trees are exposed to different levels of wildfire and drought. Now, when I concluded my summer research project, I started off with 75 tree resin samples. And especially for neural networks, this is a very small data size for training. There is a chance of a phenomenon called overfitting, where these neural networks are basically overgeneralizing on this small data set. So to test this, we used a process called leave one out cross-validation, where we essentially split our data set into one data point as our testing data and the remaining data points as our training data. Train the neural net on our training data and see what it outputs for our testing data. When we performed this technique on our 75 tree resin samples, we saw very low levels of classification accuracy on our testing data. And this is indicating of a high chance of overfitting. In the past couple of months, my mentor and I have collected up to 200 resin samples. And when we trained our neural nets on these 200 resin samples, we saw significant increases in our leave one out cross-validation accuracy. And this is coming to show that as we increase the amount of data points that we actually have in our frameworks, this is going to significantly increase the classification accuracy so that these frameworks can be really used to identify new trees and understand their corresponding burn and drought statuses. Moving on to our 2D data. Our 1D data gave us a lot of information about how the overall functional groups are corresponded with the binary drought and burn statuses. Now, our 2D data gives us a lot more spatial information about the overall tree resin sample. So potentially, there's a connection to this spatial information and the level of wildfire and drought exposure that these trees experience. When it comes to a 1D neural net, though, these typically work best for data with one dimension. Now we're working with 2 dimensions. So because of that, we can take another tool out of the deep learning toolkit. So we use convolutional neural networks. So how does a standard CNN work? We can essentially think of these cozy matrices as images, and we slide this kernel matrix across this image and perform an operation called a convolution. And essentially, the whole goal of a CNN is to basically optimize the values in this matrix that we're sliding to basically grab the most important features in the cozy data that yield the highest levels of classification accuracy. Now, when I was first learning about this topic was very difficult for me to actually comprehend. So one tool that I used to really understand a lot about the CNN architecture was through watching 3 Blue, 1 Brown videos. So if any of you guys are interested in learning a little bit more about this topic, I would highly recommend checking them out. So once again, we trained our CNNs on all of our tree resin 2D cozy data. And once again, we saw that 98 to 100% classification accuracy across all 3 classification frameworks, indicating that the CNN was successfully able to classify these trees into their respective burn status, and drought zones based on our cozy data. And once again, we compared our leave one out cross-validation strategy with the 75 resin data samples that we originally had to our 200 tree resin data samples. And we once again saw a significant increase in the classification accuracy, which goes to show that as we continue to increase the number of data samples in our data set, we will once again increase the level of accuracy, and we can successfully predict the burn and drought statuses of future test trees. Moving on to our second research question, we essentially use machine learning to really identify a good framework to classify our trees into their binary and drought statuses. But what if we try to develop a more novel method? There have been a lot of past chemical experiments out there that can successfully classify the overall chemical composition of a certain substance by using invasive techniques. But what if we leverage our machine learning knowledge to potentially develop a complete non-invasive technique of really trying to understand what's in these tree resin samples without destroying them? And in particular, one component that's very common in tree resin samples is terpenes, which are, again, part of that immunal response that these trees have. So in order to solve this in order to create this non-invasive procedure of understanding the chemicals in these samples, we decided to look into the literature and identify 18 standard terpenes that are common in tree resin samples from trees that are exposed to prolonged wildfire and drought. And we once again performed the exact same NMR experiments that we did with the tree resin samples. We consolidated all of the 1D spectral data from our terpenes into a matrix, and we consolidated all of our 2D cozy data into a tensor. Now, how do we approach this problem? We have a lot of data to work with. We have data from our terpenes and data from our tree resin samples. The goal is to find a way to bridge our terpenes data to our tree resin data. Potentially, we perform some sort of mathematical operation to our terpenes data to maybe generate some sort of reconstruction of our original tree resin data. And we decided to approach this with a technique called coefficients decomposition, where we leverage machine learning models to identify the most optimal matrix that we can multiply to our terpenes data to yield this really accurate reconstruction of our tree resin data. So here's a little bit better visual of what's actually going on in here. We have our coefficients matrix here, which consists of all these coefficients. And our belief is that these coefficients could actually correspond to the actual concentrations of the terpenes that are present in these tree resin sample data. We multiply all of these individual coefficients to each of these one-dimensional spectral vectors, sum them up, and try to generate a sort of reconstruction of our original tree resin sample data. Now, in order to generate all of these different coefficients matrices, we leverage a couple of ML approaches. The first is least squares with non-negativity constraints, where we're essentially trying to minimize the L2 norm of our residuals. And what this means is we're basically multiplying our terpenes data to that coefficients matrix and trying to minimize the difference between that reconstruction and our original tree resin data. The second is gradient descent, where we can essentially generate our own custom loss function. And this gives us a lot more flexibility. Essentially, with gradient descent and our own custom loss function, we can force the model to prioritize what we want it to prioritize. So for example, when it comes to reconstructing a 1D spectra, we care more about the peaks than we do about the baseline. So we assign a peak-weighted loss function that forces the model to prioritize reconstruction of the peaks rather than the baseline right there. And then once we've developed this custom loss function, we traverse down it in a gradient descent approach, where every single step, basically the model tries to go in the steepest decline direction to converge to this minimal loss. Finally, we use adaptive moment estimation, also known as ADAM update, which is a slight tweak on gradient descent. Rather than only going in the steepest direction during every single iteration, we sum up all the past gradients and all of the past variants of these gradients to identify the most optimal step so that we can converge to the minimum in a faster manner. So we used all three of these machine learning techniques and approaches to develop their own individual coefficients matrices. And as we can see by these results, the reconstruction was not as great as anticipated. The red lines correspond to the average reconstructed spectra that our model produced, while the blue line corresponds to the original average tree resin spectra. We believe there's quite a bit of reconstruction error, primarily because we just did not incorporate enough terpenes into our actual data set. Tree resin samples contain hundreds of different compounds. We only had 18. So in order to improve the reconstruction accuracy, we believe that incorporating more standards into this basis set will actually provide a more accurate reconstruction. Okay, so as a quick summary, what did we do this summer? We collected 200 tree resin samples and performed NMR spectroscopy techniques on all of them. This is what my NMR machine was doing last summer. It just wouldn't work too. Okay, there you go. We also leveraged a bunch of ML and deep learning frameworks to basically develop this classification framework to basically classify these trees into their respective binary drought and burn statuses based on their NMR spectra. And finally, we attempted to create a novel technique to actually understand the chemical composition of these tree resin samples using a terpenes basis. Now, what are the next steps for this project? First, we want to continue collecting more tree resin samples. And this project isn't something that's just going to last 1 year. We plan to extend this for years upon years to add more dimensions to understanding conifer health. For example, how does conifer tree resin change over periods of time after prolonged exposure to a certain environmental stress? There are a lot more answers that tree resin can provide us. And with more collection and with higher classification accuracy of our frameworks, we can get a deeper understanding of conifer health in these ecosystems. Second, we want to continue incorporating more standards into our basis set to increase the reconstruction accuracy for our second techniques that we are focusing on this summer. And finally, we want to continue experimenting with more machine learning methods. I don't know if you guys still remember, but this is Sherman Fairchild Library, and this was me on a Thursday night trying to basically fix all my code. And it can be cumbersome at times to investigate these machine learning approaches, but eventually these are the underlying answers to the problems that we're trying to focus on. I just wanted to say thank you so much to the UC Berkeley Reimer Lab this summer for giving me this opportunity to investigate these problems. The biggest takeaway that I really had was that to be a successful researcher, you need to be curious. You need to be willing to experiment and learn different techniques, and that is going to get you a lot farther in your research journey. I would also like to thank the UC Berkeley Pines Magnetic Resonance Center for funding for this project. And finally, thank you to the Caltech SFP office for providing me this opportunity. Thank you so much, and I'm willing to take any questions now.
I was joking backstage that I'd be a scientist if you were my teacher in college, but that wasn't the case. I didn't go here. Great job, Sheila. We have some questions coming in from the Slido, and so I'll just parse through and have you answer some of them. Does a model trained on one species and region transfer to another, or is each one its own project?
Fair enough. So that is actually one of the dimensions that did come into our machine learning frameworks. We basically collected samples from 5 different species, so we didn't really try to focus each of the ML models on a specific type of species, but that is also an entire research project on its own to try to see how these ML approaches change as we only focus on one species or the other. Our assumption was that the different type of species was not necessarily going to change the tree resin composition significantly, and that our ML model could basically kind of disregard any potential noise per se that would be resulting from the different type of species.
Could you catch stress before there was any visible damage to the tree? Was there like some kind of early warning system?
Yes. So in regards to the burn, for at least for the burn classification, the way that we actually classify the tree as burned or unburned using these ML approaches was we had to visibly see some sort of burn trauma. However, for the drought trauma in particular, we didn't actually visually see that these trees were exposed to drought, but our ML model was able to detect that they were exposed to a certain level of drought. And this already like tied back into the drought zone that they were experiencing. So in regards to the drought classification, it would kind of essentially be that precursor that we were looking for.
So of the national parks and the trees in the parks that you looked at, where were trees experiencing the most stress due to climate change?
Yes, I think, so I collected only around 15 samples in total. My mentor collected more of them. In particular, when I was looking at the data, San Jacinto, that was going to be a lot of where the burned trees were that she collected. And even when I actually went to San Jacinto with my cross-country trip, in a cross-country trip over the summer, and I too like quite saw like the overall health of these trees was significantly diminishing compared to when I went to Yosemite and collected the tree resin samples there. So I think for right now, I would say, at least from my experience, probably San Jacinto in particular.
What was it like to, touching on your experience of doing research off campus? Did you have fun up at UC Berkeley? Is it as fun as Caltech? What'd you think?
Well, let's just say this summer, I really am glad that I chose Caltech. No, I'm joking. I actually really enjoyed my lab. All of my lab mates were really fun to work with, and they were all so nerdy and so curious about the most random things. And I think it was a really good experience for me to just go off campus and just try research in a different institution. And quite literally, this opportunity allowed me to explore more places than even just a university. I was able to travel to national parks and collect tree resin samples, which I was really excited about as well.
And I believe, did it build upon the experience and the classes that you had taken at Caltech before that summer began?
The irony is that everything I learned in my research actually prepared me for my classes this term. So, for example, all of this research was focused on NMR in particular, and one of the hardest chemical engineering classes that we have is called Chemi 9. It's a lab class for chemies, and that's all NMR focused. So this was really good exposure for that. So interestingly enough, with my research journey in particular, it's kind of been my research has almost prepared me for my future classes, and then my future classes again prepare me for my future research. It's kind of a nice cycle.
Here's more of a technical question. Why does terpene composition change with fire stress in the first place? And do you know what the biological mechanism is for that?
Yes, so some of the terpenes actually provide a cooling response to the overall tree. When these trees are exposed to certain wildfire, they kind of need like they're also exposed to a lot more potential diseases and pests. Terpenes, they do provide this cooling response, but they're also primarily there as kind of like this immunal mechanism to protect the tree from potential future diseases that it could basically capture, especially when it's in this weakened state when they're exposed to fire.
Now, you touched on the work that some researchers, the Scandinavian researchers, had done. How do you think they knew that the drought was responsible for changes that they saw?
They collected a lot of tree resin samples. When it comes to a machine learning model, there are a lot of variables, especially for natural data, that come into play. One of the main points that they focused on was the drought. So with all of these noisy components that come into this model training, the model is able to basically generalize and focus on one specific variable and find trends in this one variable that correspond to their respective classification. So in regards to that paper in particular, a lot of variables coming into play. But if there's an overall trend within the tree resin data, the model can successfully capture it. And what that trend was that the drought status directly correspond to a different change in the resin composition.
Now we have a few more questions here, one from Joseph in the audience. Do you really use one neuron for not burned and one neuron for burned? Can't you get that information from a singular neuron?
So in regards to this one, those are specifically for the binary classification neural networks. That was the way that I approached it with. Theoretically, yes, you could use like one output node in particular for this classification, but it was just the way that we approach it. There are a variety of different types of frameworks that we can use for this project, but yes.
What surprised you the most last summer? Was it like a result, or was it something about the work itself? Was it something about you?
I think it was mostly the interdisciplinary nature of this project and research in general. I came into this project thinking that all I was going to do was collect like NMR spectra of just different tree resin samples and give it to my mentor and call it a day. But there were just so many different things that I was able to incorporate into this project. I learned not only a lot about organic chemistry, which was my initial intention coming into this, but a lot about the physics behind NMR and magnetic fields, along with all of these different computational approaches to solve all of these natural problems. So I think, to summarize, I think that interdisciplinary aspect of research is something that's just astonishing to me, and it was really nice to learn about.
We have a very nice question here that's preceded by a compliment. Great presentation. You are very poised. As a sophomore, do you know yet what you're going to do after Caltech, or too early?
Yes, so the plan is to do grad school, and the main reason for this is because my dad only had a master's degree, and I need to be better than my dad, of course. Actually, what was really nice was this project almost basically confirmed any doubts basically eliminated any doubts or any worries I would have about grad school. I really enjoyed this type of research, and I really am excited to continue this on in my own personal independent research project in the future.
Great. And before I ask my last question, I see a couple of our friends of the SURF program in the audience right now, Dr. Susan Murakami and Mr. Paul Graven. If you just want to give a wave. Thank you to you both for your support of SURF. They are members of our SURF board, which is, yes, that's the name of our advisory board, the SURF board, and I think they'd be very happy to know, along with everyone here, to hear about the great work that you've been doing at UC Berkeley, and of course you have a couple more years with us at Caltech. But what has undergraduate research meant to you during your time here so far at Caltech, and what are you doing next summer, this upcoming summer?
Yes, this summer I'll be at MIT working in Aerial First Lab. I'll be basically focusing on a directed evolution project where we're essentially trying to leverage some things that are actually being done at Caltech's Arnold Lab to a specific research problem where we're trying to engineer proteins to basically capture rare earth elements. And I think the biggest thing about Caltech and the research opportunities here is that every single PI that I've talked to has been extraordinarily supportive about my interests and my needs, like as a research student. I generally don't think that you could get such a research experience anywhere else, and that might just be due to, first of all, the absolute brilliance of the PIs in this institution, as well as the small size. So that's just like the coolest thing. Like the random conversations that I've had with a lot of the professors here has really just strengthened the overall research experience I've had here.
I was telling Sheila before the talk started that you can win the competition again. We don't have a limit on how many times you can win it. But please join me in thanking her for a great presentation. And I believe we're going to enter a quick break, but thank you to all of you for your constant support of SURF over the years, and I think it goes without saying that our office remains extremely proud of our students and grateful for the support of alums over the course of these 48 years and counting. Thank you, everybody.
Welcome back, everyone. Hope you had a great lunch, great tours, great talks, etc. Before we head into our afternoon faculty sessions, we want to recognize some techers whose work is having real-world impact. First, the Milton and Rosalind Chang Career Exploration Prize, which supports alumni pursuing ventures outside conventional career paths. This year's recipient, Philip An, BS 18 CS, for Between Human and Machine, Mapping the New Work Emerging Across Asia, a 9-month field study across Vietnam, China, the Philippines, and India to document the new categories of work emerging in the gap between human labor and automation. Published as an open access New Work Atlas for workers, educators, and policymakers. Also, Camila Boltrago, BS 22 EAS, for Phoenix Eggs, fire-activated ceramic seed pods that lay dormant in fire-prone landscapes and release native plant seeds when a fire passes through, designed to support post-fire economy recovery, post-fire ecosystem recovery, and indigenous fire stewardship in Northern California. Congratulations to both Chang Prize recipients. Please applaud them. Philip An, Camila Boltrago. And now the honorees for the 2026 Distinguished Alumni Award, Caltech's highest alumni honor, whose work has transformed their fields and shaped the people who came after them. First, we have Shula Niksad, MS 84 EE, PhD 90 APH, Chief Technologist at JPL, for her transformative work on ultraviolet technologies and instrumentation that allow JPL and NASA to investigate the deepest mysteries of the universe, for adapting those space innovations into medical tools, and for fostering interdisciplinary collaboration through the JPL Medical Engineering Forum. Please, a hand for Shula Niksad. Next, Leonidas Gibas, BS 71 MA, MS 71 MA, the Paul Piggott Professor of Engineering at Stanford and Principal Scientist at Google DeepMind, for his pioneering work in computational geometry that has shaped robots, special effects, and computer vision, for his contributions to data structures, especially red-black trees, and for his foundational work in 3D deep learning. Please, a hand for Leonidas Gibas. Thank you. Eddie W. Hartenstein, MS 74 AM, for his pioneering role in bringing satellite communications to consumers as the founding president of DirecTV, and for shaping California news as CEO and publisher of our very own Los Angeles Times. Please, a hand for Eddie Hartenstein. And last but not least, David Von Essen, BS 67, CH, Alumni Endowed Professor of Neuroscience at Washington University Medicine, for his enduring influence on neuroscience and the idea of the brain as a unified, interconnected system, for the computational tools that have transformed neuroautonomy and neuroimaging, and for his leaderstone on the Connectome project. Please join me in a hand for David Von Essen and for all of our distinguished Alumni Award recipients and 2026 Chang Prize wins as well. And one more announcement before we get back to the science. Table for Checkers is back this summer. These are small alumni-hosted gatherings for dinner and conversation in cities, around the world. What is that? Let me explain. There are just a few days left to sign up. I myself hosted one in Pasadena at my home just 10 minutes away from here last year. That fellow to my right is one of our favorite lovable, eccentric Caltech alumni. Do you know any Caltech alumni that are lovable eccentrics? Yes, you do. I've seen some right here at lunch. Okay, we did an eco-friendly theme, and so as alumni, you can choose any theme that you want. My brother Eugene, who was separating recycling out at lunch, I don't know if you saw him. I'm feeding him a grasshopper because grasshoppers are the perfect eco-protein, are they not? Yes, they are. Thank you so much. Crickets use 0.1% of the water in beef, so think about it. Think about some theme to torment and celebrate your Caltech community. So please sign up. There are just a few days to do that. It's really very fun. It's really very intergenerational. You meet people from all parts of the globe. It's as much as fun as you think it is. It's even more fun than that. So please, people here, people in other places, please consider doing a table for techers. Sign up at alumni.caltech.edu by Tuesday, May 19th, or scan the QR code on the screen right next to the cricket. Thank you. And now on to one of the oldest questions in science. How did life begin? It is the afternoon part of Alumni Day, of Seminar Day, so the jokes are going to accelerate and see which one you like better. Okay. Now, on to one of the oldest questions in science. How did life begin? Which is a much harder question than, why does the Alumni Association email me so much? That was pretty, I think they like that one. Or forget Montezuma's Revenge, will AI help me with Wordle? I think the first one was better, but there's one Wordle person there, and thank you very much. Okay. Our next speaker is Furkan Ozturk, Assistant Professor of Geobiology and Geochemistry and a William H. Hurt Scholar in the GPS Division. Furkan joined Caltech in 2025 from Harvard, where he received his PhD in physics in 2024 and won the Goldhaber Prize for his thesis on one of life's stranger patterns. The molecules of life tend to come either left-handed or right-handed, even though chemistry often allows both. His talk is about why the origin of life is and is framing a planetary problem, one that has to be approached from chemistry, geology, and physics simultaneously with constant cross-checks between the lab and field. He'll cover the state of art in early Earth environments and prebiotic chemistry. His group's recent work on a deep mystery follows as well, how chemistry on the early Earth became biology. Please give a warm welcome to Professor Furkan Ozturk. Thank you so much.
Okay, it's a pleasure to be here. I always get stressed when they tell me to give a public lecture. However, when you're talking to Caltech alumni, it's not really a public lecture, right? We are always scientifically very, audience. And I'm going to talk about origin of life, which clearly is a question that, that everyone is interested in. In fact, I was talking to my grandmother this morning, and I told her that I'm going to talk about origins of life. And then she said, what do you mean you're going to talk about origins of life? I already know the answer. And then I said, I have to go. So I came here, and first, I will clarify what I want to talk about, right? What do you mean by origin of life? What do we actually mean? So, the first genetic observation is a dog makes a dog, a human makes a human, right? A cell makes a cell. So, it's hard to imagine, a cat making a dog, right? But then we have to answer the question, where did the first cells come from, right? How can we imagine an environment where chemistry would allow for the first cell, would make the next cell, and then would make the next cell, and then animals would come, and then so on and so forth, right? So that's the question that we are going to address. And of course, we have to mention the name of Charles Darwin, who studied a portion of this question, right? That, how a human makes a human and a dog makes a dog allows for the speciation and the variety of species that we see right now. And this was in 1859, on the origin of species. He basically uncovered the mechanism of how how the evolution happens by means of natural selection. And he named the book The Origin of Species, On the Origin of Species. The interesting thing is, the only thing that is not inside the book is the origin of species, right? It is about like once a species emerge, like how it makes the other one and how like they change by subtle transformations over geological times and then create a variety of species. But the mystery of origins, the first cells like still remain, right? And then about a century after Darwin, we basically understood the genetic molecule's structure and the molecular mechanism by which natural selection and evolution happens, by the discovery of the structure of DNA, by a bunch of people, and the leading players were Franklin, Watson, Crick, and Morris Wilkins. In 1953, they discovered the structure of DNA, which is the genetic molecule that allows for information transfer. Okay? And we are about, a century after this discovery, which basically started the era of molecular biology, right? We started to look into biology into a more high-resolution way by looking into like how, biochemical reactions and chemical transformations like facilitate processes of life. And we were able to also deconstruct the tree of life, which Darwin realized by a series of field discoveries, and now we can actually do phylogenetic studies by studying the genetic transformations between species by looking at the genetic code and the genome, and we realize this like complicated tree of life. Okay, and there are like bacteria, archaea, eukarya, from which we also came, right? The plants are here, animals are here, and if you trace them all back, they go to a common origin, which we call the last universal common ancestor, which is a population of species from which everything evolved. And we know that that was a single population that we evolved from. And then the question is, right, how did the first inheritable systems that we call, last universal common ancestor emerge from chemistry? Okay, so we kind of trace all the living things back to an origin and then ask the question of how did that happen? So that was like this point, right? Biochemistry means there was like life, bio, and it came from prebiotic chemistry, which means chemistry that happened before anything biotic, pre-biological, prebiotic chemistry. And that chemistry is just like regular chemistry. The rules of chemistry, the rules of physics wasn't different. The only difference was that prebiotic chemistry was constrained by the available materials and the feedstock materials on early Earth. Okay, so it was constrained by the geochemical environments of early Earth, and if it happens elsewhere, in whatever environment it takes place. Okay, so basically the origin of life can be summarized by this following transformations of, the geochemical feedstocks under series of chemical and physical transformations produce biomolecules through the chemistry that we call prebiotic chemistry, which then, through, the series of developments of biological function becomes biochemistry. None of these are instantaneous transitions. It's a continuum, right? We cannot put any point instantaneously at this time point that we say like there is life, but basically the degree of aliveness increases from left to right. Okay? So this is about what. Now let's go to like when. So when was the origins of life? Okay, roughly like what are the like time scales that we talk about? So this is the history of Earth with some key events. Earth is about 4.5 billion years old, and this actually was discovered at Caltech by studying the isotopic decay of uranium inside like very old minerals like zirconium minerals. And then the moon forming impact happened, and then Earth started to cool down, and in which like we could have liquid oceans. And then we start seeing like the first like rocks meaning there were rocks here, but this is the oldest that we can put our hands on right now. They're about 4 billion years old. And then we start seeing the first like fossils of life around 3.5 billion years ago. And then there's a history of like really, nothingness except like very simple organisms like bacteria and archaea. And then we come to about like 500 million years ago to the so-called Cambrian explosion, where like complicated life started, right? And then the animals and everything, mammals came here. Dinosaurs like start dominating Earth about here, and then they die by this famous impact, that fell on the Chicxulub crater about 66 million years ago. And then only here, which is about like 300,000 years from here earlier, we start seeing the first humans, okay? So this is about the history of life. Like, as you see, we are here at the like sub-percent, of the history of Earth. Like everything we know, like the empires, the important events, like everything is here. And when we talk about like the origin of life, it of course has to happen before here, right? 3.5 we see undisputed evidence for life, which actually is right now you can go and see it in Western Australia. Here you see me, and here you see the oldest fossils of life, which are about 3.5 billion years old. These are what is called stromatolites. They're microbial fossils of little bacteria that try to capture the energy of sunlight, and then they get fossilized. And then you see me here, which is a product of this species. So it is kind of like a family reunion. But basically, we're talking about this period, right? Like after liquid oceans were available, let's say 3.8, and then between, we see the fossils. So pretty early on. So we asked, what, when, and now where, like where did it exactly happen? So let's look into like what early Earth was like, okay? So here you see a cover piece from Life magazine. It's interesting, right? Back in that time, they put like a cover piece on early Earth. Now you wouldn't see that. It's in 1952, where they depicted early Earth as this like a magma ocean, like a terrible place, right? It's actually called Hadean Earth for a reason. It was very hot, and it was, it's hell-like, basically. It was a hellish place. Before, it cooled down and, allowed for liquid oceans. But what were the environmental conditions like? So this is the time point that we talk about, from which we don't have any rock record. And then there was no life. There was no oxygen, which is actually a product of life, right? And then because there was no oxygen, there was also no ozone layer, which protects us from high-energy UV light. So there was a lot of high-energy UV light on the surface of early Earth. And the atmosphere was dominated by carbon dioxide and nitrogen. There was a lot of iron in the oceans. And likely there were like ocean islands, which are kind of Hawaii-like places, dispersed in a world with, big oceans. So this is what early Earth was like. And if we, ask the question like where exactly did life originate? Okay, we talk about early Earth. We basically don't know that question, but the question is related to how did it happen. Okay, so early Earth also facilitated these type of superficial environments where you could have lakes. So this is actually an illustration of the lake that was in Mars, in Gale crater. And these environments, you basically are exposed the gases on the atmosphere, and you're exposed to UV light, which can catalyze chemical reactions. And also you can concentrate minerals like phosphate and sulfidic materials by cycling of these like lakes in dry periods, which through processes called wet-dry cycling. So these environments, more benign environments, were also available, which we think were the environments that life first started. It's a local event, right? Like right now when we talk about life, it's a global thing. We see life everywhere in deep ocean, on the surface, in air. But when we talk about origin of life, we actually talk about a local event, right? A puddle that undergoes chemical transformations. And then once like cells become self-sustainable, then they can spread around and then basically form a biosphere. But when we talk about origin of life, do not think of the scale of like Earth, think about the scale of a lake. Okay, so that was the word question. So now let's go to how, right, which is a hard question. So the challenges, there are challenges to answer this question, basically. And the rock record is lost. That's one of the problems, right? We don't know exactly the mineralogy and what was there, but we have an idea. And the genetic history doesn't go as far, meaning if you kind of do the top-down approach to try to look at life and what the earliest like life was, you can basically go only all the way to like last universal common ancestor, and that is even not really possible. So you don't go to like prebiotic chemistry by just phylogenetic studies. And life is also very complicated and self-referential, meaning like something does one function and then that function affects the cause. So it is like quite circular, and it's very hard to disentangle which came first. So it's a complicated thing. And also, like right now, as we know, we have only one life, okay? Which is a problem in science, right? N equals 1 is a bad thing, right? We may have, life elsewhere and people are looking for it. And I'm always asking, how many of you believe that there is life elsewhere? Hands? Oh, almost everyone believes. Okay, like 70%. Okay. So it would be great to find another example because then we can constrain, like the environments, what kind of maybe genetic code that life form has. So it would be great to do some cross-checks about, if biochemistry is unique, meaning, let's say, the genome, DNA, and protein are the only, biomolecules that can lead to living system, or are there other possibilities? So those are open questions right now because we have N equals 1. But our goal is to understand that N equals 1, right? Our goal is to understand our biochemistry. So there are challenges, but also, there are ways to probe. First of all, life is chemical. It is composed of like 6 basic elements. We call it SNOPs: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And the rules of chemistry and physics haven't changed, right? It's the same now back and as well as on early Earth. And chemistry was constrained by geochemistry, meaning not everything is allowed, right? If you're doing chemistry in the lab to try to understand origins of life, you probably shouldn't use like gold as your reagent or very synthetic materials as your reagents because they were not abundant on early Earth, right? Early Earth's conditions and what was there constrains the possibility space. And biochemistry is the end goal that is guiding us, right? We know where we want to go, basically. Like we are not really lost in that regard. And we need to triangulate the available evidence like a detective, right? There are chemical evidence, there are geochemical evidence, there are physics evidences, and we need to basically look at them and how they fit together to constrain the problem of origins of life. And when we do that, we constantly look at multiple disciplines and the available information in these disciplines. Like when we look at this transition, as we talked in the beginning, when we do prebiotic chemistry experiments in the lab, we always ask, where can those happen? In what environments, let's say, I have loads of phosphate? And when we ask this question, those environments also bring another series of evidences, right? Let's say, yes, you can have loads of phosphate in certain lakes, but those lakes come with a lot of carbonate, which means that when you do prebiotic chemistry experiments with phosphate, you also need to include carbonate, okay? So you kind of do back and forth between different disciplines and the information within to kind of constrain the problem more and more so that, hopefully you can converge to a common scenario. So this is our methodology. So basically, the starting point is early Earth, and the end goal is biology, and the mechanism by which that transition happens is true chemistry. And the end goal, we said, is biochemistry, and we need to also then ask the question of what are the essential features of life, so that once we realize it, we know that we are alive, right? And when we look at life, the definition of life, the NASA defines life as a self-sustaining chemical system capable of Darwinian evolution. So the self-sustaining part relates to a membrane-bound thing that can catalyze certain reaction and process free energy, meaning it has a metabolism, and then it has a genome, which is really important because that makes the system inheritable. Right? It can transmit information and make its own copies. Okay, so when we look at this complex system with multiple functions like the genome, catalysis, metabolism, membrane, the role and the function of one particular machine in cells stand out. Okay, which is the ribosome. So ribosome is a molecular machine, and ribosome is a machine made entirely of RNA, ribonucleic acid, that makes proteins, which does function, and this process happens using the genetic information stored in DNA, okay? So RNA takes the information from DNA, goes to ribosome, and ribosome is itself an RNA and makes proteins, okay? And proteins then control how, let's say, DNA will replicate, how other functions will happen. So, and once you make proteins, you can do function, okay? Which we call actually the central dogma of molecular biology after Francis Crick. It's the same Francis Crick who discovered the structure of DNA. And the flow is the following, right? In DNA, you store the information, and then it gets transcribed to RNA, which is another genetic molecule, which then translates this information to the functional part, which is proteins. The problem is, how does DNA replicate? The DNA replication is facilitated by a protein, which is a replicase. It does replication. So essentially, to make DNA, you need proteins. And to make proteins, you need DNA. Okay, so which is the chicken and egg problem, which seems to get resolved by the following solution. If you can find an RNA molecule which can make its own copies, and making its own copies is a form of function, it's a form of catalysis, then you basically solve this kind of paradox by saying that the first catalyst and the first genetic molecule was RNA that transmit information by replication, which wasn't facilitated by extra proteins, but it was self-replication. And then, the functional portion became like a ribozyme, and then the genetic molecule, essentially evolved into become like DNA afterwards. So essentially, the self-replicating RNA is lifelike, okay? And that's where we want to get to. So RNA only, is not like life, but, we can conceptualize that this, this really solves a lot of problems that we kind of that talked about as the chicken and egg problem with the central dogma. So then, how do we get to a functional genome from simple materials available on early Earth? Okay, we are approaching the problem bit by bit. And now I will highlight 5 challenges, 5 problems, and one of which is the problem that I worked on extensively in the last few years, that actually were like sub-problems within that big question, okay? The big question is how do we get to an early genome under the conditions of early Earth? And that question underneath has sub-questions, and I basically picked these 5 as the most relevant and important bits. And now I will present you 5 different experiments to potentially resolve those challenges. So it's now a good time to wake up and let's see some experimental results. So the first problem is the synthesis of ribonucleotides, okay? So RNA is a ribonucleic acid made out of ribonucleotides. And if you look at a ribonucleotide, it has three chemical moieties, as we say: the phosphate part, the ribose part, which is the sugar part, and the nucleobase part. Okay? And the problem is the attachment of ribose to the base, like this bond formation, is very unfavorable. Okay? They just don't want to ligate to each other, which actually was for a long time, let's say, like a huge problem in front of the RNA world scenario. Because if you cannot make a ribonucleotide from chemistry, how are you going to make a functional ribonucleic acid, right? So this is the problem. The ribose sugar doesn't react with the nucleobase part because the chemical affinity of the base attaching to the sugar is really unfavorable. Actually, I was talking about this to a news reporter, and perhaps it's my accent, perhaps it's something else. I said exactly this thing, and then the ribose sugar doesn't react with the nucleobase part. I look at the written copy, and it says the nuclear base, and I'm like, oops. So if they come and get me after this talk, please keep going. So this problem actually gets resolved by one of the leading chemists, John Sutherland and Matt Powner, found a very interesting solution to this problem. Okay, they said why do we look at this nucleobase or ribonucleotide as composed of base, sugar, and phosphate? Okay, that's just what they teach you in chemistry in high school. Let's instead look at it from a more chemical reactivity point of view, and instead of starting from the hydrolysis products, let's start with a reactive intermediate. That is almost like half sugar and half a base. Okay, so you don't start with base and sugar separately, but you start from a molecule that you can actually make, which is half a base and half a ribose, and then you can actually attach phosphate to it. So instead of making these separately, you just made the end product, which is what we care about anyways, which became a huge deal. And this works. It solves the ribonucleotide synthesis problem, and it actually generated a complicated looking prebiotic chemical network that we call now cyanosulfidic chemistry. Okay, so that bit that I just showed is right here, right? This is the half sugar, half base molecule, which then makes the actual ribonucleotides. And then this molecule can be made from very simple beginnings, which is hydrogen cyanide. And then this chemistry doesn't only make ribonucleotides, it also makes certain amino acids and the precursors of vesicles. Okay, and the ingredients are the following: hydrogen cyanide, sulfide, iron, UV light, and phosphate. Because phosphate is also in the ribonucleotide. Well, there's a problem. Phosphate is very scarce and insoluble. Okay, so that brings us to the second challenge. Why is phosphate very insoluble? Well, if phosphate is available in waters, and it's actually available, it's just insoluble, it typically reacts with calcium ions, and it makes a mineral called apatite. And you would be glad that it's insoluble, because this is actually the material that makes up your teeth, right? Imagine you drink water, and then it slowly dissolves your teeth. But this is a problem for prebiotic chemistry, because if you don't have phosphate in solution phase chemistry, you cannot make ribonucleotides, right? It's an essential ingredient, without which we cannot conceive of life. This problem actually gets resolved by a very simple, let's say, chemical relationship, which is, yes, calcium makes phosphate insoluble by making apatite, but in addition to phosphate, if you have loads of carbonate in this environment, Carbonate basically more selectively reacts with calcium, making calcite, which is another insoluble mineral, taking calcium from the solution and leaving phosphate behind as a soluble material. Okay? So you basically find a species that reacts to the enemy more selectively, leaving this one behind. Okay? It's a very simple idea. It's not just an idea, it's actually experimentally tested. Our colleague David Catling actually went and looked into a lot of lakes on Earth and plotted the available carbonate in these lakes and the available phosphate in the dissolved form. And there's a correlation. If there's more carbonate, there's more phosphate. And in the most richest parts of the most carbonate-rich lakes on Earth, you basically have around 30 millimolars to 35 millimolars of phosphate, which is actually huge. And these are soda lakes with loads of carbonate, and interestingly, they're called Good Enough and Last Chance lakes. They're in British Columbia in Canada, which they look like this. They look very salty. But in those environments, geochemistry tells you that, under certain conditions, you can have what you want. You just need to ask the right questions. And of course, these environments do not just come with phosphate, right? You cannot just solve the problem by ignoring everything else. It tells you, well, there's going to be a lot of carbonate. And you need to take into account. You cannot cheat, basically. Right? Okay, so let's say we also solve the phosphate problem. There's another bit, which is the chirality part. That's the problem that I tackled during my PhD. So the chirality problem is actually quite an interesting one. It relates to the handedness of biomolecules. When we look at biomolecules, they're handed. Okay, there are the left-handed version and the right-handed version. And interestingly, the biomolecules only come in one-handedness. There is only right-handed sugars, not the left-handed one, and there are only left-handed amino acids, not the right-handed one. Okay, so essentially, although both of these chemical forms are available, biology basically breaks the mirror symmetry that is available in chemistry and selects only one-handedness of these molecules, which basically poses a challenge, right? If we think of life as something that started from chemistry, how can it break a rule that is in chemistry? And that's the question we asked. And the solution came from magnetic fields and the magnetization that the magnetic fields impart on the magnetic minerals on early Earth. These iron oxides were very abundant on early Earth, and they were magnetized by the magnetic field on Earth. And it turns out that if you do the type of chemistry that I just described you on these magnetized surfaces, dependent on the magnetization direction, meaning whether or not you're in the North Pole or the South Pole, you basically make mostly one-handed version of the biomolecules, but not the other. Meaning by using magnetized mineral surfaces, you can actually induce homochirality on chemistry. Right? Another simple and physical and natural solution to a problem of prebiotic chemistry. So I'll just skip this part, and I was just planning to talk about a challenge that remains unsolved, which is how do you actually connect two ribonucleotides together, because this actually connection is very unfavorable. So we didn't solve all the problems, but we made quite a progress, and there is still a lot to do. And I will just end my talk by saying that, yes, origin of life is a great challenge, but it's not intractable. And some problems are getting solved, and some of them still persist. And that's just the regular progress of science. And the field needs an interdisciplinary approach that integrates physics, geosciences, and chemistry, and feedback between them, and also a lot of experimental data, both from the lab and from field. With that, I will just end my talk by thanking my colleagues and my research group here at Caltech, and thank you for listening.
Thank you so much, Professor Ozturk. We're going to take 5 minutes of questions, and there will also be, instead of a 10-minute break, a 5-minute break. So you'll be back at 4. So we're going to check, because there's so many interesting questions. If you need to use the restroom, it's okay to zip out now and then come back, as long as you're back by 4. Okay, so then we'll start with Eric Guerin, BS 1968, because if you're here from 1968, you get 2 questions, 1968. And so I'll just give these 2, and then you can answer it any which way.
Okay.
The DNA mechanism is incredibly complex, which we are still deciphering. Does science have any hypothesis to explain how it evolved from earlier mechanisms? Second of his questions will be, what is your definition of life? So, any order.
Well, although there is no consensus, people think that DNA is actually made from like RNA. And in fact, if you look at biochemistry right now, in biochemistry, deoxyribonucleotides, meaning the building blocks of DNA, are made from the building blocks of RNA. So you first make ribonucleotides and then make deoxyribonucleotides out of them, which suggests that DNA came after. Plus, unlike RNA, DNA cannot do like as good catalysis as RNA. There are some DNA enzymes, but RNA is much better as an enzyme. So RNA basically is an okay genetic molecule and an okay catalyst. And DNA is a very good informational polymer, but it's a very bad catalyst. And proteins are very bad informational polymers, and they're very good catalysts. So, if you want to start from a so-so point, that would be RNA. And my definition of life, that's quite hard because that's, a question of semantics. It's very hard to define even, very tangible things, because basically people put more emphasis on certain things and then the other people would put more emphasis on the others. I put a lot of emphasis on heritability because, life is not just a metabolism, it's not just an energy processor, right? Otherwise, like a car would be a living thing, but it's not. Being capable of undergoing Darwinian evolution is quite a defining feature of life, and I put that at the center. But I don't have a very good definition. I think the field has a working definition, and when we see life, I think we will know it, rather than going after definition. Yeah.
The window between Earth becoming habitable and the first fossils is shockingly narrow.
Yes.
Does that mean life is easy, or are we just lucky?
Yeah. That's actually a very interesting observation, and it's actually true, right? The origins of life took much less than the complexification of life, right? It became habitable around, let's say, 4.2, and then perhaps we had origin of life around 4, which is 200 million years. And then it took all the way from 4 to, 4 billion to 0.5 billion, which is 3.5 billion years of evolution to go to complex life. So origin of life, is not a biological event, really. It's a chemical event, and chemical processes are faster than biological processes because biology needs to try, right? Biology makes a lot of copies. Some of them gets lucky and continues, and it just is a lot of trial and error. Chemistry, on the other hand, is deterministic, right? You just mix chemicals, if they're reactive, you know what the product will be, and it happens within milliseconds. So chemical transformations are very fast, and also chemicals in solution, if they're reactive by definition, and we rely on inherent reactivity of biomolecules, reactive also means that it's going to be unstable, right? Let's say you start with hydrogen cyanide, which is a reactive molecule, but hydrogen cyanide, if you just leave it, not use it, will degrade, it will hydrolyze. So once you, have enough feedstocks, the clock essentially starts ticking before you can make something productive out of it. So you need to just be fast. Is that all?
Yes. One last quick question. Do you think we'll find unambiguous evidence of past life on Mars in the next 20 years?
Okay, well, that's a question that I'm bound to be wrong, right? Because if you give timelines, you're always wrong. That's my experience. So Mars is quite interesting, actually, because early Mars, which we call like the Noachian Mars, was very similar to like Hadean Earth. And then, you know, Earth went through a lot, and it became the Earth right now. Mars almost like is frozen in time. And there's a lot of like evidence available still on Mars, unlike Earth, because Earth, again, you know, there's plate tectonics, you know, a lot of things are happening, and it's erasing information. On Mars, we can find a lot of information, and Mars probably had abiotic chemistries that resembled prebiotic chemistry. Right, prebiotic chemistry implies that life came after, right? It's prebiotic. So I don't necessarily want to call it like prebiotic chemistry happened in Mars, but abiotic processes, meaning processes that do not need biochemistry, probably happened, which are very similar to prebiotic chemistry on Earth. And I personally don't think, you know, like there is life right now on Mars, but, you know, that doesn't mean that, you know, maybe protocells were made on Mars and they just, for some reason, didn't sustain and didn't create a biosphere. It would be very hard to find life in that case because it would be very like, you know, scarce information instead of like a global spread of life. But Mars gives us a very high resolution data, both geochemical data and also like planetary science data about understanding origins of life. So I think we should continue like sample return mission from Mars, which is on pause right now, unfortunately.
Thank you so much, Professor Ozturk. Big hand. Thank you. Welcome back. Just 2 more sessions, and they're both exciting ones. Before dinner, all right, now we travel from early Earth to modern pandemics, which we're all too familiar with. Our next speaker is Pamela Bjorkman, the David Baltimore Professor of Biology and Biological Engineering and a Merkin Institute professor. Pam joined the Caltech faculty in 1989 after the kind of training resume that's hard to summarize quickly. As a graduate student in Don Wiley's lab at Harvard, she solved the first crystal structure of a human MHC molecule, which is foundational for modern immunology. I hope that's one, okay, let me do that joke again. I hope that one's on your LinkedIn profile. Okay, continuing. Pamela is a member of the National Academy of Sciences, and last year she received the Wolf Prize in Medicine. Please give a big, warm, rock and roll welcome to Professor Pamela Bjorkman.
Okay, thank you very much. It's a real pleasure to be here and to speak in front of such a distinguished audience. So what I'd like to tell you is the attempts of my lab to create a COVID-19 booster shot that would actually, we think, prevent another pandemic from starting from a sarbecovirus spillover, which I'll define in a moment. Okay, so first, let's just talk, we all lived through the COVID-19 pandemic. That was, of course, caused by a virus, which is SARS-CoV-2, which is a coronavirus. And the whole point of that virus and any virus is to deliver their genetic material, which can be either RNA or DNA, which you heard about in the last talk, to the host cell, and then they have to take over the host's machinery to produce their own proteins. And then they assemble new viruses, their daughters and sons, in the infected cell, and then they release the progeny to infect other cells. So because viruses are small compared to our own cells, they're parasites. So the genomes of viruses, whether they're RNA or DNA, are quite small compared to, say, a human cell, which would be 6 billion nucleotides or so. But coronavirus genomes themselves have about only 30,000 nucleotides. So they can't encode everything they need to reproduce. So viruses have to hijack host cells, and they can only reproduce if they force the host cell to make viral copies of themselves. So what happens then, as I said before, is new viruses leave the host cell and they infect similar cells, and then not all viruses actually cause disease, but some viruses do cause disease. Okay, so unfortunately we're all too familiar with this, but there were zoonotic sarbecoviruses. A sarbecovirus is a SARS-like beta coronavirus, and of the coronaviruses I'm listing here, which all spilled into humans from animal reservoirs, of all of these, 2 of the human health emergencies that you've heard of, the original SARS epidemic and the SARS-CoV-2 pandemic, were caused by sarbecoviruses. And these ones outlined in blue they've been around for hundreds of years, or some even thousands of years, caused common colds. And then there's MERS, which is still circulating through contacts with camels, but it's basically kind of wiped out. Okay, so the reason I'm worried about another sarbecovirus spillover is that it's happening all of the time. So these are 2 papers that I'm listing here from various groups, but the one I'll talk about most is this one from 2023. So what they did is they surveyed communities in rural Myanmar to look and see if they had any evidence that they were being infected with sarbecoviruses. And in fact, about 12% of the people they screened between 2017 and 2020 were positive in their blood for exposure to sarbecoviruses. So they were being infected all of the time. So what these authors conclude is that exposure to diverse sarbecoviruses among high-risk human communities provides epidemiologic and immunological evidence that zoonotic spillovers from animals into humans are continuously occurring. So I believe we need to prepare for the next sarbecovirus spillover. It's happening all the time anyway. We can't stop that. But the thing that causes a pandemic is when you get a spillover where the virus is able to transmit easily between humans. So the ones that are transmitting now just happen not to transmit well between humans. And in fact, why was this epidemic here in the early 2000s nowhere near as bad? There were only about 8,000 people infected here as opposed to the millions infected with SARS-CoV-2. The reason really is that the original SARS was transmissible between humans, but not until they were symptomatic. So they were usually in the hospital at that point. Unfortunately, SARS-CoV-2 evolved the property that it could transmit between humans before they were symptomatic, and so we all know the result of that. So what we're proposing is a COVID-19 booster shot that could prevent another pandemic. So in order to explain this, here's some basic biology about viruses, or about SARS-CoV-2 in particular. So that's a schematic. It has RNA inside it, so its genetic material is RNA, and then it has these spikes on the surface, and the spike has to bind to a receptor on a host cell in order to infect. And that receptor is a protein called ACE2. It's critical for regulating your blood pressure, but it happens to be used by this particular virus to enter host cells. And then it gets in, it makes copies of itself, and it makes more proteins. More viruses. Okay, so the interesting thing that I'm going to come back to at the end of the talk is that this is actually what the spike looks like in a higher degree of accuracy than just this schematic right here. So it's a trimer, so that means it has 3 identical copies of proteins. And then it has 3 receptor binding domains, which I'm going to refer to throughout this talk as RBDs. And those only bind to ACE2 when they're in an up position. Okay, so it means that the RBD is able to go up and down like this. And that, I think, is the reason that we would be able to actually make a vaccine that could prevent another pandemic, as I hope to explain at the end of the talk. Okay, so most antibodies that are neutralizing recognize the spike RBD. So what do I mean about neutralizing antibodies? It's some kind of, antibodies are immune proteins that circulate in your blood and actually go into your tissues, but they can neutralize a pathogen by preventing it from entering. So for example, if you have an antibody that is this Y-shaped molecule here, it will be important that it has 2 arms later, So if it stops the virus from entering, then that stops all the subsequent steps. So if you can make a vaccine, most vaccines work by preventing viruses from infecting most cells so that you stop them from becoming factories to produce more viruses. Okay, so when the pandemic started, Christopher Barnes, who was then a postdoc in my lab, he's now an assistant professor at Stanford, he solved a lot of three-dimensional structures of the SARS-CoV-2 spike protein bound to various neutralizing antibodies that were isolated by our collaborators at Rockefeller from COVID-19 convalescent donors. So up here, these structures, and then down here later that were induced by vaccines. And I won't go into a lot of the details here, but the spike protein is going to be light gray and dark gray, and that's the trimer. And then the various antibodies are these different colors right here. And they bound in all these different ways, and we tried to figure out what was going on. But we soon discovered that some of these bound to conserved regions of the RBDs. So when I say conserved, I mean that if you look at sequences of sarbecovirus proteins across animals and SARS-CoV-2 proteins that were infecting humans, if you look at their spike sequences, you found regions where the amino acids were the same and regions where they kept changing. So we all know about these variants of concern, for example, where there's been mutations to change. Well, most of those are in this receptor binding domain or RBD region. Okay, so here is the strategy that we're trying to do. So if this movie runs, okay, so that's a surface representation of the structure of a spike trimer. The RBDs are in yellow now, and this is a more detailed view of what the actual structure looks like. That's a down RBD. That's the difference if this RBD is up. Purple means more conserved across sarbecovirus sequences. Orange means variable across those sequences. So look, you can see a real difference in the distribution here. Mostly at the top do you find the orange or the variable parts, and mostly more at the bottom do you find the more conserved parts. So we did a bunch of these structures, and we found, yes, people were making antibodies that bound to the more conserved region, but they weren't making that many of them. So what we wanted to do is shift your antibody response so it preferentially binds to those purple regions. And now, no matter what spills over as a sarbecovirus, or no matter what variant of concern comes up, the antibodies you've made already from a vaccine or from from a vaccine should be able to protect you. Okay. Okay, so how are we going to do that? Well, we've developed something we call a mosaic strategy, and I'll define that in a moment. But the idea is the way you make antibodies is you go into lymph nodes and you interact with cells called B lymphocytes or B cells, and those have a membrane-bound version of an antibody, which is called a B cell receptor. Okay, so this orange thing is representing the membrane. And if you make a typical vaccine, what you would have gotten is not exactly this, but it would be similar. The point is that all the receptor binding domains are the same. So now what's going to happen is the antibodies that are membrane bound that are on the surface of that B cell will preferentially bind to what we're calling strain-specific distracting epitopes, which are the orange triangles. An epitope is just a region of the antigen, where an antigen is what is recognized by your immune system. Sorry for all the jargon. But what you're going to get is mainly strain-specific antibodies, and those will work as long as there's no changes in that orange part. Okay, but what if instead of injecting that as your vaccine, you injected what we'll call a mosaic nanoparticle? This one has 8 different types of receptor binding domains attached. And now, look, these orange B cell receptors cannot cross-link between adjacent strain-specific distracting epitopes because those triangles are all different colors. And instead, what you would preferentially, we theorized, activate are B cells that produce these purple cross-reactive antibodies, because in order to bind with both arms, they have to cross-link between the purple regions, which is the part that's a little bit harder to make the antibodies against. Okay, so that was our theory. So Alex Cohen, who was then a graduate student, now a postdoc in my lab, what he did was he picked 8 different sarbecovirus RBD sequences from various human or animal SARS-like beta coronaviruses, and he made a mosaic 8 nanoparticle. And it looks like that, and it's got 8 different RBDs attached to it. It has 60 positions, and so that's the mosaic 8. And then we also made, for comparative studies, a homotypic nanoparticle. That's the one that I showed you should preferentially elicit the orange antibodies against the variable regions. And so then we did all kinds of animal experiments to look at what types of antibodies are raised. And the idea was we would look for matched responses, and that means that the mosaic 8 nanoparticle included an RBD that is represented by whatever we were actually looking for, binding or viral neutralization. We also looked for mismatch. That's the most important thing. We're trying to look for responses to viruses or just binding responses to viral proteins from things that are not represented. So that's the whole point of this, is we want to induce the cross-reactive responses whether or not the RBDs happen to be represented on the nanoparticle or not. Okay, so in these studies here, we were able to use 2 different animal models, and we showed that the mosaic RBD nanoparticles protect against both matched and mismatched challenges. So these are viral challenges. You vaccinate an animal, and then you challenge it with a particular type of virus. Okay, so the first one was in non-human primates. We injected mosaic 8B nanoparticles, and it protected the monkeys against SARS-CoV-2 Delta and also from original SARS challenges. Both of those are mismatched. They're not represented by RBDs on this nanoparticle. Okay, so then, because you can't get that many non-human primates to do these studies, we repeated this in a mouse model where you can infect mice if you've introduced the gene for human ACE2 into them, and now they can be infected with SARS-CoV-2 and other sarbecoviruses. Okay, so what we did here was we immunized with either mosaic 8B or with the homotypic SARS-2 in these mice. And it turned out it protected against both matched and mismatched challenges. The mosaic did, but the homotypic did not. It only protected against SARS-CoV-2. So the punchline here is that the mosaic 8 nanoparticles protected against SARS-CoV-2. That was a matched challenge, but it also protected against the original SARS, which was mismatched. The homotypic nanoparticles, yes, just like the vaccines we get now, it protected against the matched challenge, which is SARS-CoV-2, but it did not protect against SARS-1. So here, since we can't predict what type of sarbecovirus might spill over, we're using SARS, the original SARS, to represent an as-yet unidentified sarbecovirus that could spill over into humans to start another pandemic. Okay, so why does this work? Are we actually eliciting a different type of antibody response with the mosaic nanoparticle compared to the homotypic nanoparticle? So to address that, we used a technique called deep mutational scanning, where we can introduce all kinds of mutants, substitutions in the receptor binding domains, and then you map out where the antibodies in an antiserum elicited in a mouse or a non-human primate, where they're actually binding. And the red regions demonstrate where they're binding. And what we found was for the mosaic 8 immunizations, they elicit antibodies against conserved regions. And I'll just put this conservation gradient here up again. So remember, the orange is the more variable parts if you line up all the sequences across sarbecoviruses and SARS-CoV-2 variants. And the purple regions are the more conserved regions. And so what you can see if you go back and forth here is you're getting more of these antibodies to the purple regions, but it's shifted up to these orange regions when you immunize with the homotypic. So that validated our approach that we were shifting the antibody response. Okay, so then people have asked me repeatedly, well, fine, but if you target the conserved or the purple RBD regions, won't they just start to mutate and then we'll be back at square one? Well, I don't think that's going to happen, and that's based on a fundamental fact about the structural biology of the SARS-CoV-2 spike, which I alluded to at the beginning. Remember that the spike contains these 3 copies of the receptor binding domains, and this is the orange and purple gradient is here mapped onto a down RBD. And these are, when it's down like this, the purple parts are actually hidden, but it has to go up. So it has to expose those hidden parts to the immune system every time it binds ACE2. It can't help that, it's part of its life cycle. So if you actually map, this is a surface representation of the RBD in 2 different orientations, and you've seen the variable and constant depiction of the sarbecovirus sequences here. And if you look at where are the purple regions, the more conserved regions, they map almost exactly on the blue regions, which are contacts that the RBD makes to other parts of the spike when it's in a down position. So sarbecovirus spikes really cannot easily mutate these purple regions. So that's why I think it might be possible to actually make a vaccine that would work against any sarbecovirus that spills over and against SARS-CoV-2 variants of concern that might appear. Okay, so let me say that we'd like to turn this into an mRNA technology because that's a protein-based technology and those are harder to manufacture. So an RNA vaccine works by, you take lipid nanoparticles that encode the spike protein, let's say, for the Moderna or Pfizer vaccine. That gets translated inside the cell, and you get cell surface expression of viral spikes, and that makes antibody responses and another type of response called T-cell responses. But Magnus Hoffman, then a graduate student and a postdoc in my lab, he invented a way to actually also secrete virus-like particles. So you enhance the efficacy of an mRNA vaccine by doing this. So this is induced by host proteins here, and we've demonstrated that it works for a number of other types of viral spikes and also host proteins, and you get better immune responses. Okay, but can we actually make a response? Can we make a vaccine like that that incorporates this technology, which we call EABR, which stands for the host proteins that it recruits in order to make those secreted virus-like particles? So can we actually make one of those? Well, it's somewhat difficult because these are mosaic 8, so you'd have to have 8 different RNAs, and that's not that easy for various reasons. So we adopted a quartet methodology. So we make RBD quartets. So if you have 2 quartets, you have 8 RBDs. And so this is the normal way we make mosaic 8 nanoparticles. We just attach RBDs to this 60-mer nanoparticle. But if instead you attach 4 RBDs in a row, these are called quartets, you can adapt that for attaching to a protein. And this is easy for technical reasons to turn into an mRNA vaccine, and in particular, an mRNA vaccine that adopts this EABR technology to secrete these virus-like particles. So we believe that if you got a mosaic 8 RBD-based vaccine, in particular, it would be easiest to give it as an mRNA vaccine. If you got that as a COVID-19 booster, it would provide increased protection from SARS-CoV-2 variants. It would also protect future sarbecovirus spillovers from causing an epidemic or a pandemic. But the protein-based mosaic 8 is very difficult to manufacture. So we've taken sarbecovirus RBDs arranged as 2 membrane-bound quartets that can be genetically encoded, so that can be given as an mRNA vaccine. And we've shown that these mRNA immunogens can present these dual RBD quartets at the surface of the cells, or also on the surface of these released envelope virus-like particles. And we showed that these elicited equivalent or superior antibody responses and increased T-cell responses. So in other words, as good or better immune responses. So with that, I'd like to thank you for your attention and point out the people who've actually done this work, in particular Alex Cohn, who started the Mosaic 8 approach, Christopher and Cheng Cheng have done the structural studies, and Magnus Hoffman developed the EABR approach. So thank you for your attention.
Thank you so much for that, and we have questions absolutely flooding in, so let's begin. Could this approach work for influenza, RSV, Ebola, or other pandemic threats?
Yes, we believe it could. We're trying it right now with influenza, in fact. There are technical reasons that it might not work as well, and that's based on the fact that, unfortunately, influenza, RSV, Ebola, Andes viruses also, the hantavirus that we keep hearing about, they don't have a spike protein that does this strange thing of having up and down portions of their proteins, of the proteins that are required for entry into a cell, and that's the reason that we can target conserved regions. So we're actually trying to do very controlled experiments with an influenza virus antigen called influenza hemagglutinin and test, because that doesn't have up and down orientations of its receptor binding domain. So we're actually trying to see if that's the case. But certainly you could make mosaic nanoparticles for all of these.
Why do some vaccines prevent catching the virus, while other vaccines only help reduce symptoms?
Well, the actual fact is, I think we all needed to learn this, and that includes me too. Vaccines do not prevent you from getting infected. It's just that that infection is either asymptomatic and you don't know that you were ever infected, but your immune system kicks in earlier and so you don't notice it, or they prevent severe disease and death. And so when you get an influenza virus, when you get a flu vaccine every year, sometimes people get the flu, but it is reduced in severity. So there are no, what you're asking about is, are there vaccines that induce sterilizing immunity, meaning that you never, ever, ever get infected? And most vaccinologists and virologists believe that that doesn't exist. Some of the closest things you can get to are the measles virus vaccine, that's quite sterilizing immunity. It appears to be anyway, because there's anecdotal evidence that like a ship came to the Faroe Islands and kids and adults got the measles. They were introduced by the sailors, and then 60 years, so they'd never been exposed before, and people died. But then 60 years later, another ship comes in with measles, and the people who were old enough to have been exposed did not get apparently sick. But there's some evidence now that there were probably asymptomatic measles viruses spreading amongst them. Another, perhaps almost sterilizing immunity is the human papillomavirus vaccine. But no, the COVID-19 vaccines were developed to prevent COVID-19, which is the disease. They were not developed to prevent SARS-CoV-2 infection. That's the virus.
Eduardo Kutolenk, thank you, asks, based on your targeted delivery mosaic system, can a structure-based vaccine be created that restructures prions without causing a catastrophic systemic response?
Oh, you want to make it with prions? I have never thought about that. I don't know how to answer that because we've never considered that. The nanoparticles we are using are completely and utterly innocuous. And so and they actually work to accomplish what we're trying to accomplish, which is to get B cell receptors to cross-link between adjacent conserved units. So the geometry is correct. So we don't really want to switch to another platform except for mRNA, which is so much easier to manufacture, and we've shown through a variety of experiments that those also can cross-link to induce the responses against the conserved epitopes.
What would be the timeline to human trials? And what's the you're chuckling, that's it. What's the manufacturing like? Easier, harder, different from mRNA?
Well, the history of this is we did have a funding from this the Consortium for Epidemic Preparedness Institute, or CEPI, and that's an international organization. And we had like a $30-some million grant to manufacture the Mosaic 8 RBD nanoparticles as proteins, and we had a clinical trial on board, and we had someone at Oxford who was going to conduct that clinical trial. We had the proteins manufactured. They were all set to do toxicology studies, and then they could have been manufactured in the amounts needed for the clinical trial, and CEPI cut the funding in December of 2025. So I think there is now very little enthusiasm. The idea is, oh, well, COVID-19 is over. What I'm trying to convince everyone is, it might be over, but sarbecovirus spillovers are not over. And so I think we're desperately need to have something like this to prevent, if we happen to be unlucky enough again, that another sarbecovirus spills over and it can transmit easily between people when they're asymptomatic, we're going to have another worldwide pandemic unless we prepare for it now. We are trying very hard to get funding for a clinical trial. It's extremely expensive for the protein-based. That's why we switched to the mRNA-based. We could do it for as little as $10 million. We just have to get that $10 million from somewhere. But we're trying to get it from the Medical Research Council in the UK because, frankly, we're not going to be able to get it from the United States government.
This next question is always a concern on this topic. It's from Erdnis Sangachiev. Apologies if I mispronounced your name. How can we effectively counter anti-vaccine claims, such as the belief that vaccines cause autism?
I don't know, except by continually showing real data. There are many studies now where there is no correlation whatsoever between vaccines and autism. I mean, the problem is that some children who get vaccinated develop autism, and children who do not get vaccinated develop autism. It's sort of like if you get a vaccine and the next day you get hit by a car, is the reason you got hit by the car because you had the vaccine. And so I think we just need to, people are afraid, so we need to try and speak what we know to be truth. There's a lot of literature. There is no linkage between vaccines and autism. There was unfortunately a paper that was published like 10 or 20 years ago now that claimed there was a link because of the thimerosal, the mercury-based adjuvant that was in certain types of vaccines. And that paper was retracted because it was found to be false. But that idea has not gone away, unfortunately.
Klaus Makauka, BS 76, we welcome you, ask, would periodic booster shots be needed?
Yes, I believe so. And it's not because you have to change it. Like, the reason we need periodic booster shots for COVID-19 booster shots now are for two reasons. One of them is the immunity tends to wane, but the second one is we keep getting new variants of concern, so there's mutation. So the vaccines don't work as well because your immune response is to the older variant. We take care of that second problem. Your vaccine response would be okay for any variant that came up in theory and any sarbecovirus spillover that happened. So that's why we're saying you could get this as a COVID-19 booster, and then if there's another spillover, it should stop that from circulating around the world. Now, whether or not the immunity would wane, it probably would, because most vaccines don't last for a really long time. The measles virus vaccines and human papillomavirus vaccines last for decades, but most others don't. So we'd have to do human trials in that case to figure that out.
Dean Dogger, PhD, asks, how would you anticipate or test for possible side effects of your booster shot design?
Well, there's So the people who run these clinical trials test for all kinds of things. Their reactogenicity, like do you get a sore arm? Do you get a fever? Do you get chills? Do you have malaise? And so they rate these on certain scores and things like that. Now, are there worse side effects? If you've heard of the thrombocytopenia that was apparently linked to certain types of the COVID-19 vaccines from Johnson & Johnson and also AstraZeneca, these turned out to be linked to people who had this certain immunogenetics. They encoded certain types of MHC molecules that you mentioned before. They happened to make a response, an antibody response that cross-reacted with their heart, and so that it was very rare. It was extremely rare. But you don't want that. You still don't want that at all. But you've got to do a clinical trial where you test for side effects. So that's a phase 1 trial. You test for safety. That's what would have to be done. It's safe, we know, in non-human primates and rabbits and mice. But we're trying to test it in humans now.
Eduardo Kutelenk again. How do live virus vaccines differ from inactivated virus vaccines concerning the binding receptors?
They would almost certainly use the same receptors to bind to, so they would have some kind of spike protein or something like that. The viral entry protein would bind to the host cell receptor in that case. The inactivated, the inactivated vaccines, it depends, this is all complicated here. Let's say you get an inactivated flu virus vaccine. That means that it's never going to infect your cells. Instead, it's going to be taken up by antigen-presenting cells and basically eaten up and then presented to your immune system, and then you make responses. Live attenuated vaccines, when they're safe, tend to be more effective, but they can also cause problems as well. So there are some live attenuated vaccines that have been used for years. The yellow fever vaccine that was developed in the 30s is an example of a live attenuated virus. So they grow that virus in another animal. In this case, I'm pretty sure it was chickens, until it infects you, but you no longer get sick from it. Instead, you develop immunity. So there are no live attenuated COVID-19 vaccines to my knowledge. And these are not, by the way, like mRNA vaccines are not so-called inactivated vaccines. They're a different technology.
With all we learned from the COVID pandemic, do you think we can see a hantavirus become a pandemic, take a similar course like COVID?
Well, I'm not an expert in this because I'm not an epidemiologist or a physician. I really don't think so, because the transmission is so much harder. So I'm sure you've read these things about the cruise ship and things like that. So there was another hantavirus outbreak in 2019, and if you read about that one, somebody had been like exposed to mouse or rat droppings, and when they're aerosolized, you can get a hantavirus infection. But that stops dead in its tracks unless it's one type of hantavirus, which is called the Andes virus. That's the only hantavirus that can spread between people. Well, this person got an Andes virus infection, goes to a birthday party, and wasn't feeling real well, but spread it to 6 people. And then they tracked those people down when it was figured out what was going on, and they quarantined them. And at that point, unfortunately, the time to which you get sick can be 1 to 8 entire weeks. That's why people have to be quarantined for so long for the latest hantavirus problem on this recent cruise ship. But after that, it was gone. People are getting hantavirus vaccines, infections around the world, but they're not creating epidemics or pandemics yet, and I think based on the way they transmit, that's very unlikely.
Randomly arranged spike domains. What does that mean mechanically? Are they actually random, or is the arrangement selected?
Oh, Well, we can't prove that because we can't use any form of electron microscopy that's high enough resolution to tell us exactly where they are. There's 60 positions, there are 8 RBDs. Are they arranged randomly? We believe so from controlled experiments where we take just one type of RBD and we put it on all 60 positions, and we do that for the 8, and we ask, do these couple with the same efficiency? The answer has been yes. So we assume they're arranged randomly, but we've done a series of antibody binding experiments that correlates with that. So we believe they're arranged randomly, but there's no form of imaging we could ever do that would prove that beyond a shadow of a doubt.
I think that's the last question. Thank you so much, Dr. Pamela Bjorkman, that fascinating Saving the World talk. Thank you so much. Greetings, checkers. We close seminar day today with, okay, one last joke. Please, I'm going to say one sentence. It'll be followed by another sentence. Then I'm going to go like this and then laugh really hard. Okay? You ready? Thanks. Thanks a lot for that. Okay. We close today with a question that sounds like a riddle. What would it mean for a material to behave like both a solid and a fluid? And no, we're not talking about my stomach after too many vegan ribs at lunch today. See, they are alive. They actually are. It's not animatronic. They are alive. Vegan ribs. Isn't that a bit of a contradiction? But how delicious were they? Thank you. All right. Our last speaker today is Chiara Daraio, the G. Bradford Jones Professor of Mechanical Engineering and Applied Physics and a Heritage Medical Research Institute investigator. Chiara designs new materials with mechanical and sensing properties that don't fit our usual categories, work that has shown up everywhere from the New York Times to CNN, and which she also pursues as a director of research at Meta Reality Labs. Please give a big, warm end-of-day welcome to Professor Chiara Daraio.
All right. Well, good evening, everybody. Thank you for coming and for being here. I do realize that this was a long day for all of you, and I'm the only thing that separates you from dinner, hopefully not vegan ribs again. But you are also the only thing that separates me from going back dancing with my husband after 15 years. So let's make the next 45 minutes worthwhile. And I promise I will bring you through a journey of challenging materials understanding and intuition, as we know from our basic studies and your past time at Caltech. So I've been at Caltech for about 20 years. Actually, this year marks my 20th anniversary. And my research group over the course of these 2 decades has really been working at the interface between material science and primarily mechanics. We work on both fundamental challenges that really truly challenge our common intuitions and definition in material. And we also work on more applied work that aims at solving engineering problems that use these new materials and this new fundamental understanding towards applied engineering. After all, what has drawn me to materials is really the fact that when I was studying mechanical engineering as an undergrad, I realized that materials really have historically marked and defined the evolution of our very own civilization. So advances in technological innovations, whether it is in optics, mechanics, or medicine, really rely on the advancement of materials and the understanding of what makes them special. So today, I'll bring you to a journey that will elucidate how the behavior of architected arrangement of matters that in the jargon of the literature is called metamaterials can be strikingly different from the raw materials in isolation. More is different, borrowing from condensed matter physics, not just as you go from scales of atoms and condensed matter, but also as you go from materials to architected materials or metamaterials, which derive their properties not primarily from the solids which they're made from, but also from the geometry and the topology of their microstructure. Okay, so let us start from the familiar world of solids and fluids. There is a key distinction in our intuition and imagination, is that solids have a fixed shape and they have fixed properties, of course, unless you think of them in geological timescales, while liquids tend to flow and rearrange. And sand and rice or coffee beans are a bit like liquids or fluids. They flow and they take the shape of the container they're poured into, and they have one particular property, which is they have no resistance to shear. So the transversal force applied to them, they oppose no resistance to that. So I have two kids, and I was watching this cartoon. If you haven't seen it, or if you have kids or grandkids, I recommend watching it. There's a question that says, what if materials could behave like flowing grains in one moment and solid blocks the next on demand? This is taken from a Disney movie called Big Hero 6, and it effectively envisions the possibility of transforming something from a solid to a fluid on demand. Well, it seems rather far-fetched, but having something like this would allow us to create systems that, for example, change shape on command, adjust their stiffness, and repurpose their functions as we please. Think about opportunities, for example, in different scales, from the micro scale for example, robotic surgery, all the way to the space dimensions, thinking about reconfigurable solar arrays, for example, in outer space. It turns out that this is actually a property of biological matter which is actually rather common in biology. The video you're seeing here, it's a video from the literature, not from our group, but shows how materials, in this case, the marvelous example of morphogenesis of a fruit fly embryo, shows that a collection of cells can work in unison to shape different tissues and ultimately form a fruit fly. The secret is the collective motion of these many individual cells that operate in concert, flowing, condensing, and stiffening as required to give life to a fly. So this happens in nature, but how can we engineer this solid-fluid duality into synthetic materials for engineering applications? So let's start from the beginning of this journey, which is the idea of these architected materials or metamaterials. Usually when we think about our studies in physics in high school or in college, we think of materials as monolithic blocks that effectively have fixed properties. Think about a block of steel, for example. It doesn't change shape easily. But to do that, you need to think about how you can fragment these, like the cells in the embryon, into separated functional units. This is the concept of metamaterials. It takes a bulk, and then it conceptually fragments it into units that can be designed individually using, for example, computer or numerical simulations in 2 and 3 dimensions. And then advanced fabrication tools, such as rapid prototyping, 3D printing, and other evolving manufacturing tools, allow us to then fabricate them at different scale, from the micro to the macroscopic scales. Here is an example from actually 10 years ago, how engineers can use metamaterials to create objects with targeted functionalities. In this slide, you're seeing the classic Stanford bunny, a toy model for computer graphics. The bunny's body has different colors, and the colors on the left represent different properties. Think about it as different stiffnesses in the body. Using metamaterials, it is possible to tile or 3D print in one go, for example, the bunny, that has different holes pattern in its volume, not just the surface, in order to ensure that the bunny can have bouncy feet, for example, a floppy here, or even actuate these parts when the materials become responsive to external stimuli. So this brings us to the need for diving a bit deeper in the difference between what we understand as a solid and what we understand as a fluid-like materials or a granular material. So if we start let's start from looking at a solid. When you think about a solid, think about, in this case, an eraser or a rubber band. When you apply a force to the solid, it responds with a deformation, right? So if you can stretch the rubber band or whatnot. Now, in a solid, whether it's very stiff or not, you always have this deformation or a displacement of the volume, both in tension and in compression, because you can pull on something or compress it, and you have, most often for common solids, a symmetric response. At the contrary, fluids have a very asymmetric response, because think about sand, for example. When you compress sand or you walk on it, it has a response very much like that of a solid, in that you compress it and there is a slight displacement. So on the compression side of this curve, you see that it mimics the response of an actual solid. But of course, in tension, they respond with no resistance, because you can pull sand grains apart. Turns out that there is another class of materials that, for the purpose of this lecture, I'm gonna call in between continuous and discrete material. I'm gonna call them discontinuous materials, which effectively are a bit of a mix of the two. So a classical example is a chain, or in fact, in 2 dimensions, a chainmail. Now, in these discontinuous materials, the particles, instead of being sand grains or coffee grains, are catenated and linked with one another. And they effectively have freedom to move, both in tension and compression, until the rings, in this case, come into contact, both in tension and in compression. So you can see that they have a very in-between response, in which you have first a zero response, like the granular fluids, and then once they engage, when the ring engage, both in the compression or in tension, you have this elastic response that's similar to a solid. The combination of this confined motion and elastic deformation hides a very powerful response that defies the conventional materials physics. There are no theories today that really explain the response of these systems, while these systems are very common, in fact, in our everyday life. Well, perhaps the oldest example of exploiting, probably just by pure empirical trial and error, are chainmails. Chainmails are the earliest form of metal armors that were worn by the soldiers during the medieval era. Interesting, medieval chainmails were developed almost simultaneously in the East and the West. This particular example is a 15th century example of European riveted mail. And they were an advantage, although they were very heavy. This particular example here was about 10 kilograms or about 20 pounds to be worn. They provided protection against being cuts and sharp points and blades. However, they were very good at protecting from blasts, for example. So why do they work, and why were they an advantage, other than the fact that, of course, the rings were made of steel? Well, it turns out that granular particles, not only they flow, like I showed in the example of the glass, but they also have a properties you may be all very familiar with. They undergo something that in physics is known as a jamming phase transition. You probably experienced it when you bought coffee for your coffee machine. When it's tightly packed or vacuum packed, it's effectively like a brick. It's very, very stiff and rigid. But when you cut the packing up, again, you can put it into your coffee machine very easily. This phase transition, it's an interesting one, because in physics, it's dependent entirely on the topology of the distribution of the grains, not in a temperature response, which is the conventional phase transition in most known materials. Instead, these local geometric constraints control and dominate the response of granular matter. When unjammed, you can, for example, apply a shear stress or a transverse stress, and the particle would flow freely. But when they're jammed under, for example, vacuum packing, they become solid, like in this transition you see here. So we thought, perhaps we can exploit this transition by combining the idea of architected materials, as I explained them at the beginning of the talk, and then combine them into creating a modern form of medieval chainmail. In this case, the difference is that we can use advanced computer designs for replacing the rings in the medieval shapes with more complex octahedron frames, for example, or any cage frame particles that exploit effectively the freedom of design of solid. You can then take these particles and connect them. These wire frames can be connected in different topological locking arrangements, creating sheets, for example, of particles that could be squarely or triangularly packed or whatnot. These topologies convey very interesting properties to the 3D printed chainmail. For once, they're very lightweight. They're primarily void. So this particular example you see here is only 20% of material volume occupation. So the chainmail that you saw in the prior slide would be, instead of weighing 10 kilos, they would weigh about 200 grams or half a pound. And they can still conform and shape around the human body. The one you see in these slides is, by the way, it's 3D printing in one go, so it requires no assembly with a nylon printer. And so we thought, just like the medieval counterpart, these modern chainmails could be folded around the body or draped, and like coffee beans, could be jammed to become solid. And so what we did is to study first with in this video you see here. This is called level set discrete element simulations. We can take a layer or two layers, in this case, of chainmails, compress them at the boundary, and make them jam like the coffee beans. This enforces a phase transition that creates a transfer from a soft, unjammed state to a stiff, load-bearing state. And just like that, we can exploit this behavior to create materials that can be shaped into different geometry before being jammed into load-bearing structures. And we, in this particular case, demonstrated we demonstrated two geometry, but we have since developed many more solutions. And so you can think about, for example, materials that change shape and stiffness at different scales, from wearable orthopedic supports to larger scale deployable structure that could, for example, be transported easily, rolled into a more compact domain, and then deployed to create temporary emergency shelters or bridges for disaster relief. But this was just the beginning. When you think about the capabilities we have from computational tools and now even AI-driven tools to design in 3 dimensions, the space for exploring these complex architectures of linked particles is effectively limitless. So we can also have almost limited ability to manufacture shapes that go well beyond the medieval ring design. This video, for example, shows a very creative idea that allows us to exploit topological knot theory in the mathematical world to generate effectively linkable particles that can then be tessellated into ever more complex topological chainmails. Why is this important? Well, each one of these designs carry dramatically different jamming properties and self-locking abilities. Just like puzzle pieces, they can basically self-frustrate and prevent deformations in different directions. For these, and to really confine the research for the material geometry and the space of parameters possible, we developed theories that effectively study the geometry and the topology of the interlocking to predict how and when these kind of interconnected elements can be load-bearing or flexible. And we have the derived generalized rigidity criteria, if you're familiar with the well-known Maxwell criterion for structure, to predict, for example, foldability, stretchability, and load-bearing support. This was effectively reducing this big parameter space that would allow us to create structures like the top that cannot deform, or the bottom that instead deforms freely when compressed. And this is the theory. It's relatively simple, but getting there, it's a few pages. So everything I told you so far, though, really was limited to one-dimensional chains or two-dimensional chainmail, which is fine, but not very practical. To truly arrive at materials for engineering applications, we need to really move to 3 dimensions. And for this, we introduced a class of materials that consists of discrete concatenated rings or cages particles interlocked in three-dimensional networks, forming polycatenated architected materials, or PAMs. PAMs are a new class of three-dimensional materials that are semi-continuous or discontinuous and bridge the gap between solids and fluids. We describe them as effectively particles that are made of, or materials that are made of three-dimensional particles that form very intricate 3D networks of force and stress distribution. So how do we get there, and how can we design them? Well, translating lattices into polycatenated PAMs can actually borrow a lot from basic chemistry. If you remember from your chemistry classes, you can think of molecular structure, especially crystalline structure, as network architectures that are, in general, ordered and periodic. Think about, for example, the network you see here on the left. This is the classical diamond structure. Now, you can take any one of those chemical structures in 3 dimensions and extract the network topology, and then select suitable shapes, like, for example, these tetrahedron or cuboctahedrons, and then use the same linking topology to create effectively 3-dimensional materials, like crystals. These are some of the designs of the many, many thousands of designs we've produced that can then be additively manufactured using, for example, multi-jet fusion fabrication processes that can be extended from polymeric structures, soft gels, all the way to steel or titanium systems for more load-bearing materials. In this particular case, you're seeing all examples made of the nylon samples you saw before. The labeling actually borrows from crystallography. Because we're borrowing on this network topology of crystalline structures in chemistry, we can also borrow on the symmetries and crystal structure analysis that chemists do conventionally. This allows us to classify a family of materials, polycatenated materials, and study them in bulk rather than from case by case. One of the things that's interesting is that these polycatenated structures, just like in the one-dimensional case, have many degrees of freedom. The kinematics plays a very important role on how they deform under different conditions. They can, for example, rotate, they can shear, or they can translate, just like I showed the example in 1D. The result is a set of materials that are extremely counterintuitive in the way they react to stimuli. So what you're seeing here is one example of the many, many we have in the lab, again made of nylon, which really has the feeling of holding a gelatin block, but when you compress it, it's exquisitely rigid, almost like compressing a vacuum-packed rice pack. So what can we do with this, and how do we go about studying this? Well, one thing for sure is that just by the look and feel, these materials are really fluid-like. And so we study the fluid-like response just like we would study a fluid. We look, for example, at the droplet wetting case, in that we can create droplets of these polycatenated materials and see how they so-called wet a surface, depending on how far they spread on a table, for example, in a planar state. And the change, in this case, it's the same geometry and the same crystalline orientation, but just the thickness of the rings is increased or decreased to make it more or less wetting. They can also take the shape of the container or not, depending on how we design the topology of interlocking. But to prove that more quantitatively the fact that these materials in fact behave either like a solid or a fluid, we can perform mechanical deformation tests. In this case, the standard test is a shear test. What I told you at the beginning of the presentation is that fluids generally have a zero response to shear or to transverse motion. In this particular case, you see a sample of a polycatenated architecture that is exposed to shear on the left and right dimension. And here we measure the force response, or in this case, the stress as a function of strain. And you can see that for the entire time that the particles are free to kinematically slide on top of one another, the material, the bulk piece of material has a 0 shear response. And then once the particle all engage and come in contact, the stress response become elastic. So it transitions from a fluid-like to solid-like. And this is true for many, many of the packing and family of symmetries that we tested. One interesting application for this is looking at impact response. So let's look at these two videos. This is a drop test of a weight. So in this case, you're looking at a steel ball being dropped on a solid, fully compacted or fully interlocked system. And you see that the material behaves rather brittle. It's again nylon. The particle strikes it, and the block responds like you expect. But when you look at the PAMS in its fluid state, you see it almost splashes, like you would expect from a solid. Why is this an advantage? Well, the advantage is that the kinetic energy of impact and the momentum are basically, instead of being transferred to the solid and then transposed or transferred to the bottom where we have our sensor, they get redistributed over a big big network of force chains that also dissipate energy, not just from, for example, viscous damping of the materials, but also from friction between the particles. This brings us to a reduction of force transfer, which is rather dramatic. And it's, in fact, surpassing any other foam that's used, think about protective element of sports gear in many applications. We're, in fact, exploring a lot of these possible applications, both for a liner of helmets. We're working with the Army for looking at landing gears of drones that can land on non-flat surfaces or conforming effectively to rough terrains when landing, or even thinking about robotic skins that would allow effectively a response much more similar to the one in our own skin. Now, we can make these polycatenated materials also at a micro scale. So we can use tiny 3D printers, or in this case, 2-photon lithography, to make them many times smaller than the examples I showed you in the rest of this talk. In this case, for example, for simplicity, you can think of the scale of each one of the particles in the prior videos and movies you've seen to be about 1 centimeter. We can make them so that, in fact, the scale of the particle is about 200 microns. This is the thickness of your hair. So imagine making rings that are the thickness of your hair and then interlocking them into these architectures. When we do that, the surface to volume ratio changes dramatically. So in these materials, the surface is much, much larger than the prior case. And this allows us to exploit different other properties, not just the mechanical properties, but multi-physics behaviors, such as electrostatic interactions. In this specific case, you see these polycatenated materials that is then copper-coated and then fabricated at the millimeter scales. What we can do this is effectively create something that's conductive so that we can exploit the response of the surfaces to electrostatic charges generated by a Van der Graaf generator. And in this case, the presence of charges of the samples causes the rings to repel each other and expand. This is the result. Just like in the video of the Disney cartoon, we can have effectively materials that when electrostatic or electrical field is applied, can respond and actuate on command. Interestingly, when the materials are actually down and relaxed, they're very soft, fluid-like. But when they're actuated, like in this case, they become rigid and stiff and load-bearing. We're exploring possibilities, and this is really work in progress, to use some of these materials also in more complex geometries and architectures, such as these tethers and tentacles, that allow us to envision the possibility of using these, for example, for smart catheter or microelectronic devices for medical intervention. So more is to come. This is just scratching the surface of what architected materials can do. But a lot of this work really wouldn't have been possible without challenging the common intuition and definitions of what we know and think about solid and fluid, and thinking about materials that can be both solid and fluid on command. So with that, I should thank you guys for listening, thank the funding agencies that made all this work possible, and the research group who has been supporting this work, particularly Dr. Wenjie Zhao, who's been very much involved in the design of polycatenated material, Sujika, who is working on the protective helmets with polycatenated structures, Huji, who develops the theory and the mathematical intuition for the design, and Professor Yifan Wang, now in Singapore, who has really started to work on the three-dimensional chainmails you've seen at the beginning of this talk. So thank you all for listening and for staying until the end, and I'm happy to answer any questions.
Thank you, Professor Daraio. Fascinating. Eduardo Coutolenc, one more question of the day. How can and this is a great Caltech question, I just love the language of it. How can non-Hermitian systems enable programmable quantum geometries to circumvent conventional jamming phase transitions through different control mechanisms? With vegan ribs. No.
Oh boy.
You want me to say that again?
I have actually no idea.
I love that. Yes, thank you. So that's a crowning glow. That's like
we have. Well, I mean, the reality is that we haven't really explored analogies of large-scale system to quantum system. Although I know that there is the potential to do this because this system, in fact, have nonlinearities that can be akin to the optical nonlinearities that are of interest in let's say, quantum computers. My group hasn't really explored that, but I know others in the literature and other colleagues whom I meet at conferences are looking at those problems. I forgot the second part of the question.
Okay, well, let's try. How can non-Hermitian systems, what are non-Hermitian systems? I don't know. Enable programmable quantum geometry to circumvent conventional jamming phase transitions through different control mechanisms?
Yeah, I think the right answer is I don't know.
Okay, I love it. Okay, thank you. Okay. Are there any files we can use to 3D print this at home?
Oh, absolutely. If you actually reach out to me, I can send you the files in 2D, 3D. I think you need to have a special kind of 3D printer because it is a little tricky to print interconnected rings that are effectively freely moving. Because if you think about it, when you 3D print something, you need support materials. You cannot 3D print anything that is suspended in free space. So we use, for example, jet printing because it uses powder beds to support. So if you have a powder bed printer at home, by all means you can 3D print this. To be honest, tip of the day, there are services online that you can send this to, and they'll just send you the 3D print back for maybe 10 or $20.
You can do this at home. All right.
Yes.
Okay, and then, my Slido just went away. And it was about interlocking particles. Okay, hang on one second. Help. Here, 4 questions open. Here we go. How do interlocking particles avoid entanglement friction? Does the geometry just prevent contact?
Right, so that's actually a good point. Friction, in many cases, can be your friend, like in the example I showed here for dissipating energy. But in other situations, for example, in the actuation example I showed in this video, friction is not your friend. So how do we prevent? Friction is always there. Whenever you create a real three-dimensional system, friction is going to be there. The way we prevent it is in 2 ways. We can design the effectively geometry and topology of these systems in order to avoid contacts unless contacts are truly required, so that you really exploit the kinematic degrees of freedom of the topology. And 2 is by really trying to be very careful in the surface treatment. So this specific case, for example, uses, you don't see the size, but uses polymeric materials that then are coated on the surface with a very, very thin nanolayers of copper so that you can a little bit change the friction and surface properties on demand. So the answer is you can change the frictional properties by either controlling the topology of the interlocks or by controlling the surface properties.
Ken Deist asks, have you thought about space-based applications, and if so, which ones look most promising?
We haven't yet truly explored the possibility in that this work is really relatively recent, and so we've been really trying to dive more in the theoretical understanding of the mechanical deformation and ways to design and predict the responses before really exploring all the range of applications that are possible. The only real application we really explored so far is the wearable protective systems for sports, for example, sports equipment. But I think there is a space in which these kind of interlocking materials are useful in outer space because the point is they can be transported in a very compressed space, so they can be really packed, jammed very, very tightly, and then deployed like in the example I showed at the beginning, in which there was a layer that was rolled up and then deployed, for example, into different shapes. So I think there are opportunities we just haven't quite yet explored. Also, they're extremely good at absorbing vibrations, just like the shock absorption, and that's a big problem in space. So I could see advantages not just in the lightweight and compact packaging, but also in their ability of absorbing vibrations.
Could you dynamically switch PAM behavior with power input and control it?
Yeah, so the example of the video of the actuated micro PAMs, in fact, it's switched with electricity, right? So we're switching on and off a voltage, and that creates these electrostatic charges that can make either the volume expand or contract. We've been thinking about different ways to actuate or trigger these. For example, we've been thinking about magnetic actuation. In other cases, we've also been thinking about using responsive polymers, for example, polymers that can swell when wet or in the presence of, say, different pH. And these would also allow us to, for example, by either thermal stimuli or by adding water or by adding different kinds of salts, control the expansion and interlocking. But this is still very early research.
How do PAMs fit into the XR space, like with haptics or soft robot?
Good question. I think they don't really. I mean, I think maybe the closest example is this idea of soft robotic skins. I would say it's very futuristic as an answer. But because they can be sheared very easily, our skin also can be sheared very easily. That's why we can pinch ourselves so easily. And so some of these PAM's properties are better than any other, let's say, monolithic polymers like silicones, because silicone it has a different response to shear. But the downside is that they're still rather expensive to make. So even if you can order them online and get your sample at home, I think for large volume manufacturing, these materials are not quite ready for prime time. So I don't see an immediate connection between the two. But who knows, maybe in 10 years.
Dean Dogger, PhD. Have you compared this work to Shen Chen's lab at Caltech? They gave a talk at 2024 Seminar Day about natural motil devices.
I don't know this work.
Aha, it's right here at Caltech, so that will be
I
a walk.
should.
After you
Shame on me.
After you go dancing with your husband, you can go visit the Shen lab at Caltech.
And watch back the video from 2024. Apologies, I'm not familiar.
You just walk across the mall. That's the beauty. All right, well, on that, yes, and you have an anniversary to celebrate, and thank you so much. So on that note, please give a warm hand to Professor Chiara Daraio. Thank you so much. And wait, for those of you fleeing, we have a few important reminders. Thank you. Today we went from mathematical proofs to molecules, from early Earth to future pandemics, from student research to materials that behave like two things at once. In other words, a typical day at Caltech, just with more vegan ribs. It's been a privilege to host you today and share a stage with some of the world's most interesting scientists. To officially close out our 89th annual seminar day just a quick 2 minutes, please welcome Mario Peraza, AVP of Alumni Relations. Yay.
Huge round of applause for Sandra, again, for thanking and for being our moderator for our MC for Seminar Day. So thank you all for joining us, and I hope you really enjoyed the 89th Annual Seminar Day, hearing from fascinating faculty and, of course, our brilliant students around lunchtime. Mark your calendars to continue the conversation in October with our Fall Alumni Weekend programs, October 16th through the 18th. And that's it. Now, please go out, enjoy. We have dinner out on the mall for you, some food, some wine. We'll be out there till about 6:30, and have a great evening.